cool little soundboard over here. Give me a second though. Okay, so perfectly set up to do some excellent work on things. How does it actually sound? Let's test it on YouTube. Do some excellent work on things. How does it actually sound? Let's test it on YouTube. Okay, hopefully it works. Why is it so trash? I don't know. Okay, let's just do trees. Okay, let's lock in and do some trees. Trees. You cross my heart, convert tree into sorted. Let's go. Let's go.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem, search.
All right, so I've just got an empty workspace here.
I'm doing this. Fuck, I'm doing all of it. All of it.
Hey everyone, welcome.
But the issue is I don't have the... I have all the time in the world. I can do anything I want. Minimize the tree, put it back house. Okay. Go back. Go back. Yeah, let's do this. Convert sorted array into binary search tree. Given an integer array nums where the elements are sorted in ascending order, convert it to a high balanced binary search tree. I need to convert it into a high balanced binary search tree. What does that mean? Output 0 shook. Well, what does it mean? Also is accepted. Why? Why does it make it high balanced? I don't get it. Should I just switch the bottom leaf? Is that what it means? Let's try. None of this shit. Okay, let's see. Fuck. you.
Hey everyone, welcome back and let's write some more neat code today. So today let's finally solve a slightly easier question, convert sorted array into a binary search tree. So we're given an array where every number is sorted in ascending order, and we want to convert it to a height balanced binary search tree. And by height balanced, they just mean that any subtree has a difference of height of at most 1. And the reason they want it to be a height balanced subtree is because, well, given an input array like this, technically we could just make a tree where every single node doesn't have a left child, but it has a right child. So basically it would end up being a linked list, right? And that would be the easy way to do it. But they want it to be an actual balanced binary search tree similar to the one that they have drawn over here, right?
So this is a balanced binary tree. What's the difference? So this one is basically left. How's that? I don't get it.
So since they want it to be balanced, notice how we chose a 0 to be our root. Why did we do that? Well,
Wait. What's going on? How is that a binary tree, bro? Into binary, convert sorted array into binary search tree. Is this what I did? Convert it to heights balance. Convert it. Okay, this is sorted array. Okay, I need to change it into a. I don't get it. Oh, I get it. I need to make it. I still don't get it. What? Why is it? Why is it called this way? Don't get it. Don't get it. Don't get it. What am I supposed to do?
Why you bullying me?
What am I supposed to do? God, help me.
0 is the middle value, right? And what that means is these values will go in the left subtree like we have over here, and these values will go in the right subtree like we have over here. And so notice if we choose 0 to be our node and these are the values we want to go in our left subtree, it's a recursive definition, isn't it? Like now our job is to take this smaller sorted array and create a binary search tree with them, right? So we can solve this problem pretty easily using recursion. Let me show you how. So we start with the same input array with 5 elements. We will put a left pointer here and a right pointer here. This is going to tell us the subarray, basically the elements that we're using to create a tree. Then we're going to find the midpoint, right? We can do that with our left and right pointers, and we'll find that this is the midpoint. What are we going to do? We're going to remove this element, or basically not consider it anymore, because we're going to create a node from it, right? So 0 is going to be our node. Next, I'm going to create with these elements a left subtree for our root node. So what I have to do is get rid of this mid and move this right pointer to the position to the left of mid, right? So then we can actually use this subarray. And using now these 2 pointers, let's recompute the mid. Does it really matter whether we choose this or this? It doesn't. So let's just put our mid to be at this node. So now 3 is going to be the root of our subtree, our left subtree. And once again, we're going to update our pointers now, right? So we know that we don't really have any more elements to the right for this subtree. So we're going to take our right pointer and shift it to the left and create a left subtree from this single element, right? And so since this is basically the base case, right, left and right are together, meaning mid is also going to be in this position, we know that the left child of this of -3 is going to be -10. In reality, our algorithm is going to have a different base case. Now we're going to continue for this -10. Let's see if we can have a left subtree for it. We know there's not any elements over here, but we're still going to try. We're going to try and move our right pointer over here. Now, this is the condition that we know that we've done something wrong, right? Our left pointer is somehow greater than our right pointer, right? Our left pointer should not be to the right of our right pointer. So this is basically the base case, meaning we're going to end up returning null. So meaning the left and right child of this are going to be null, right? This is a leaf node. So now that we've created nodes with these elements, let me not forget to actually connect this. So now that we've created this subtree, we're going to return, and the root node 0 is going to know that this is what its left subtree is. But we have another job left to do. We have to create a right subtree for our root node.
1,000 problem solved with elite code shirt. Can you believe it, man? Oh yeah, okay. So so solving 1,000 elite code problems, getting a elite code t-shirt. Started here with like 63 days of elite code, a max streak of 6 days based. We got again 70 days, again no consistency. Got my job in 2020 and I didn't need to do any elite code at all. I don't even know what happened here. I guess maybe I was getting sick of my job after 1 month, or maybe I was just doing it with coworkers. I have no idea. That's kind of a weird thing, right? To see a lot of elite code here, or maybe there was like some kind of competition or something. I don't know. Within the company, it's basically empty. My least active day. Then 2021 was the day I decided to leave my job. I live streamed all of this in 2022, about 3 years ago. Did it every single day almost. And then we kind of like slacken and then got our offer and then gave up again. But today marks the biggest. Quit my job, did some leak code.
Bro, my one is going to look brutal. Yeah, it's not that bad. Not that bad. It's just like sometimes I go on a different tangent. Or sometimes I don't like I do it in a different app. I come back, do it here.
To maintain, and then we went ham today. Feel like a dozen one sites. I don't know what I'm doing wrong. Yeah, I would say that a lot of people are, at least for me, I feel like, and one thing I fell into this trap, so maybe it's just me, but the behavioral questions, I didn't realize how much harder behavioral questions are. Like, just the whole interview process is way harder. You need better behavioral stories. You need to answer your questions better, and you also need to answer the technical questions better. So like, it's like both. So like, you can be on an on-site and they'll ask you, they'll ask you for your elevator pitch. So it's like reframing your elevator pitch. So it's like act slightly harder to get the job thing, like forward. The number one thing in basically in this journey has been like, the leak code problems are really hard. Rabbit hole is really deep. They're essentially that there's really hard leak code problems. Two, I think most people fail because of most people aren't like disciplined enough. I don't even think it's about motivation. I think it's just like in real life / applicable situations. Okay. Have you looked at the OA Obez had? No, I have a similar profile. It's a direct good problem. So like to give it, there's like basically before this react is, and tricky is like weird or things 1,000 people don't even do. I think it's pretty clear ones who pretty hard to test BFS and all that stuff, that like they'll test you this stuff on interviews, but like because it's second nature, you can write it in like 2 minutes and you can write it without any bugs. There's like a little memorized like template in your head for it, and you just can kind of read off of it. But like even deeper than that, it's like innate, I guess, like just from.
Bro, that's such a flex. Look at, bro, 1,000 lead code problems. Holy. Thousand. Oh my god, that's difficult. 1,000. Come on. That's like, I think I can do 300 before. I enjoy some of them. I'm not gonna bitch about it.
Or what with like
Can I complete 1000 lead code problem? Probably, right? I could. Theoretically, I could. No. And it's not a good thing, let's be honest. 48 problems a day, which would mean no deep learning, massive burnout. You'll be clicking and submitting, not learning. Okay. Being interview ready. If done properly, in 3 weeks. Oh my God. Okay, let's do some. I want to go in like proper order. Not that it actually matters, but I wanna, let's see. Same tree. Let's do same tree. I want to check if P and Q are the same tree. It's not. So how would I go about it? So I need to do it recursively. So I need to call. I need to use a. Should I do? So I need to call. What should I do? God help me.
Why you bully me?
So I think I need to call the same thing again. So let's do is same tree, and let's actually do something that's outside the box. Let's think outside the box. So I need to go here. So I need to call the thing. So if not root, return false. And I need to call, how do I call this? If same tree, if it is the same tree, let's actually look at the solution. Iterative DFS, fuck off. Iterative, bro, breadth first search. Depth first search. Oh. So I need to check. Yeah, this thing. Okay. I have the template in my mind. Okay, if q dot root and it's p and q. So let's go p. Let's go bam 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 bam, and let's go q dot root is equal to. If both are equal, we need to go. P dot and P dot right is equal to Q dot right. I need to call it though. Fuck. What should I do? How do I call it? Fuck you. Okay, I need to return it. Okay, fuck you. That makes sense. Return to if P and Q, P dot value Q. This needs to be true. This needs to be true. This needs to be true. I need to return left and right. Okay. And P. Okay. Fucking what is R? Fucking retard. q dot val is equal to p dot val. I need to return q dot is same tree tree. The value I should what value should I pass on? It's got to be left. Okay. Q dot left branch, left node, left root. That will be used as a root, whatever. And q dot left and q. Let's use this shit because why not? P dot right, comma q dot right, else return false. Bro, can these shit ass fuck ass fuck you, P. Should I do self? I hate self. Okay. Should I submit it? Same tree. Fuck you. I'm gonna beat the fuck out of you, but I'm not copying though. I was not copying at all. That was not copying at all. I did not copy. If anyone says that I'm copying, I'm gonna beat you with the fist of God. What am I looking at? I've done it. Let's submit. What? It's not equal, so it should return this is false. That shit is false, my dude. Yeah, I don't know why. Right here, P, Q, because what's the, I think it returned true because this fuck ass PQ bullshit. Okay, that's sweet. Okay. Balanced binary tree. Let's take a look at it. It needs to be balanced. What does balance even mean? 1, 2, 3, null, null, 4 is equal to, okay, it's true. Why? Is it balanced? Balanced meaning, is it like balanced that way? Okay, how do I check if it's balanced? So if it has one or more, if it has two or more, okay, if it has two trees, then it's, so if not root, if not root, return false. And what is going on? What's okay? What's this? How do I check if it's balanced? Why would you do that? That's so. Why max? I don't get it. Max. Bro. Nah. I think I did this in the thing too. Did I do this? Nah, I haven't done it. Let's just do it. It doesn't make sense.
Hey guys, Greg
It doesn't intuitively make sense.
here at Let's Solve Balanced Binary Tree, LeetCode number 110. So we're given a binary tree and we need to determine if it is height balanced. And what that means is, well, a height balanced binary tree is a binary tree in...
Give me a second.
which the depth
Okay, let's do
depth of the two subtrees of every node never differs by more than 1. Now that sounds kind of confusing, so let me show you an example. Okay, if we were given this tree, this actually is height balanced, so we'd want to return true for this. Now, if it is height balanced, it means that its right height, which happens to be 1 here, and its left height, which is 2, the difference between its two heights, 2 minus 1, and we actually want the absolute value of that because we just care about the distance between those two things, that is equal to 1, and so that is at most 1. So as the definition said, as long as it's less than or equal to 1, then that means it's good to go. Okay, but we need to check more than that. We're not just talking about the root here. We need to make sure it's balanced everywhere. So the root might be balanced, but there might be an issue elsewhere. Let's check the other nodes. Well, if we look at this node, well, its left height is 1, its right height is also 1. The difference between those things is just 0, and that is also less than or equal to 1, so that is okay. If we were to look at any of these three nodes, well, all of their left and right heights are both 0, so all of those are going to be zeros. The difference between 0 and 0 is just 0, so all of those are balanced as well. So because all of these different nodes, all of the nodes in the tree are balanced, therefore the whole answer would be true. If we had a tree that looked like this, well, now if we look at the root here, the root would have a right height of 3 and the left height would be 4. So it's comparing 4 to 3. The difference between that is just 1. And so there's no problem in the root here. And there's actually no problem here either. That's comparing 1 to 2. That would be fine. But there is a problem if you're talking about this tree. So if you're rooted in this tree right here, if you're rooted in this, well, its left height is 1. Its right height is 3. And so just for this node here, the difference would be 2, which again is bigger than 1. And therefore, since there is a problem somewhere in the tree, there is a problem.
Where is balance tree actually? My mouse keeps dying like a bitch. Reused in, let's see.
Overall, and so our total answer would be false. So we'll assume that it's balanced through this global variable, and we'll do our DFS here, and if we kind of ever find that, oh, here, there's actually an issue here, well, we would change this to be false here. And so that way, once we kind of came back from our DFS and we were done our helper function, after we're escaping this, we could check if we're balanced or not. If we ever turn it to false, our total answer should be false because there was a problem somewhere. Otherwise, if there wasn't an issue, well, then it just should be true like it was before. And so we can just kind of return the value of this global. Okay, so let's actually just assume that we are balanced, and you actually want this as the list of true. If you don't know why, I explained this thoroughly in the diameter of a binary tree video, but in general, you would want this to be a list when you're talking about a global variable, instead of like a local variable to the recursive function. Okay, then we're going to write a recursive helper function that's going to basically return the height of a tree. So it's going to return the height of a root. Now, if we...
Is that the best way to do it? where is it actually used? Iterative. So recursive and iterative way to do it, but I think recursive is better for DFS. So this is the recursive iterative. Look at how retarded it looks using stack. I don't like the iterative approach at all. It's fucking retarded. Is it a better time complexity though? And iterative is n. Okay. What about h? Ooh, the best case is really good. Space 2 is Space 2 is better. I think let's look at this. Let's look at this objectively. Using a left and right, left DFS search, right DFS search, balanced 0 and 0 and isn't this? If it is, what is 1? What the fuck is 1, bro? Return balanced, comma, whatever that means, whatever this shit is. I don't get it. Like, what the? What the hell, bro? It is DFS. Definitely DFS.
We don't have the root, well then we want to return 0 because a non-root shouldn't contribute to the height. Otherwise, we need to get the left height is equal to the height on the root dot left. And we also need to get the right height, which is equal to the height of the root dot right. And now we can immediately say, hey, if the absolute value of the left height minus the right height, if that is ever bigger than 1, well, then that means there is a problem. And if there is a problem, we want to set our global, so you need to do balanced at 0 is equal to false. So now that we've done this, if there was a problem anywhere, that means there is a problem overall, and our complete function here, this function should return false. So we set that to be false, and now there is always a problem. Now, if that is actually the case, we really don't care about the height of our function anymore. And so I'm just going to return 0, because if you've set the fact that there is an issue, well, then we know at some point we're going to end up returning false. And so we really don't care if our height thing is actually working at this point. It's already going to return false. So we'll just return the value of 0 in that case. Now, otherwise, if we haven't ran into an issue, well, then we just want our function to return the height. The height of our current node is going to be 1 plus the max of the left height and the right height. Okay, so this function is called height because it's returning the height.
Is it, bro? It's kind of difficult. I'm not going to lie. I can get it, but it's like, let's try. Balanced. Give me a balanced height. Why don't you fucking do that? Balanced. Okay, let's create another function. What am I going to put it in here, though? I should put in root, of course. I can see it. Bro, what the hell? This is like really difficult. Diameter of the binary tree. I need to use PFS. PFS.
What kind of skill set is achieved after you solved over 1,000 problems on LeetCode? Is it true that after you solve 1,000 problems on LeetCode, you are absolutely cracked? Right? That is to say, after you solve 1,000 problems, there's nothing that you can't conquer. You've seen it all. You've seen dynamic programming, linked lists, circular linked lists, singly linked lists, doubly linked lists, heaps, priority queues, depth first search, breadth first search, uniform cost search, union find, quick union find, weighted quick union. You've seen it all, right? Can you solve any problem? No, you can't, right? Because the sad reality is that all of us have a certain amount of intellect, right? There's this IQ score bell curve, and you're somewhere on that bell curve. Now, what solving 1,000 problems will provide you with is the capacity to move yourself a standard deviation above, or maybe a standard deviation and a half, something like that, above where you're actually at, right? So it pushes you significantly, but it's not going to make you an absolute 10x engineer who will get into Google and Facebook and you know, put your favorite company's name here, right? It's not gonna do that for you, but it will put you in a position where you can push yourself to the next level. Okay? And that's all that is really necessary for an average person like myself, right? Because, you know, I've kind of, you know, guesstimating here, self-assessment, that from doing over 1,000 problems, I'm in a position now where if you give me an easy problem, I can solve it probably 95% of the time, right? If you give me a medium problem, I can solve it probably 70% of the time. And if you give me a hard problem, I can solve it probably we'll say 30% of the time. Okay, so what's the probability that I'll get a roll with that kind of metric? So let's just imagine I'm in a situation where, you know, I solve 3 leak code problems, right? So I solve one and it's the first one they give me is easy, the second one they give me is hard, and the third one they give me is, the second one they give me is medium, the third one they give me is hard, right? That means that statistically, I'll pass 20% of interviews. And you might say 20%, that's a failing number. So if they give you an easy, then a medium, then a hard, you're only gonna get through 20% of your interviews? What if I told you that's sufficient, right? Because if I go do 10 interviews, look at that. Your boy's got the job. So it's really a numbers game, right? You could be an average engineer, do a lot of problems to put you in a position where you can't solve everything. You can only solve 30% of hards. But if you just play the numbers game, right, assuming that you get an easy, I'm in a situation where, you know, I roll with that kind of metric. So let's just imagine I'm in a situation where, you know, I solve 3 leak code problems, right? So I solve one and it's the first one they give. I'm in a situation.
I'm 6'2". I go to Stanford University. I have 10-inch penis.
Situation where, you know, I solve, right, do 20 interviews, right? 2, 3, 5, 1. What was the other number? I already forgot. 2, 4, 0, 0. Kind of what the problem.
1,000 problem solve with elite code.
I've solved a lot of leak code problems.
500. Bro, 300. It's not that much. It really isn't that much. It's crazy. People are flexing 300 like it means something. Fucking hell. It just isn't that much. Okay, that's easy. Nigga, give me easy. Fuck you now. Breadth for search is tripping me out. Balanced binary tree. I don't get balanced binary tree. I don't get it. Bro, I just wanna difficulty. You difficult. They have a formula to all these binary trees and shit like that. They have a formula. It's a Catalan formula or something. And for the tree diameter, they have a formula too for a binary tree. But I think graphs are different from trees. So and graphs are like unidirectional and trees are like top down. Cousin and binary tree. Okay, give me like a high percentage filtered by acceptance. Okay, given a root of a binary tree, convert it to a greater tree such that every key of the original binary search tree is changed to the original key plus the sum of all greater than original key in BTSD. As a reminder, a binary search tree is a tree that satisfies these constraints. The left subtree of a node contains only nodes with keys less than the nodes. What the hell? The right contains only nodes with keys greater than the node's key. Okay. 15, 21, 30, 30. How's this? What? 36. Oh, just like minusing it. 36. What the hell? What the hell is going on here?
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem convert binary search tree into a greater tree. So we're given the root of a binary search tree and we
The internet, it's a strange place, okay? It's the only place I know where a small event can happen and every last person's like, it's so over or we're so back. And that just happened again, okay? We're talking about a massive one. I saw videos being made, tweets being had, people just telling me all of software dev is somehow over again.
We might be 6 to 12 months away from when the model is doing most, maybe all of what SWEs do end to end.
Hey, do you see this? This is me. Some sub-millisecond analog. A lot of these people are now apparently making some sort of cryptocurrency and then also rugging people. We'll get back. Okay, that's...
Big surprise. Five, bro, it's not even that much.
want to convert it such that every key of the original binary search tree is changed to be the original value plus the sum of all values that are greater than that one in the binary search tree. So for 4, we want to add to the original value, which is 4, every value that's greater than it, which is going to be 5, 6, 7, and 8 in this case. If we add all of those together and add it to 4, we get a sum of 30. So we want to replace the original value with 30, and we want to do that for every single node in the tree. Now remember, this is a binary search tree, not just a regular tree. So this has some properties that are going to be useful for us. So for a node like this one, where are all the greater nodes going to be? We don't have to search through the entire tree to figure out the...
What is BST? BST sound like some sexual thing. Strap on or some shit like that. I don't know. Okay.
Topic is binary search trees. So in this video we'll learn about binary search trees. So in this video we'll learn about what is binary search tree and the properties of binary search tree. So here is a binary search tree. Let me define it. It's a binary tree in which for every node, all the elements in its left subtree are smaller than that node, and all the elements in the right subtree are greater than that node. So if you look at this also, elements in the left subtree, there's only one element that's smaller, and here the element is greater. For this node, this is smaller and this is greater. So this binary tree is useful for searching. That's why it is named as binary search.
Binary search tree. Okay.
How it is useful for searching, I'll explain. Suppose I'm searching for a key value 40. Then
Okay.
Start from root. Search for 40. Is this 40? No, 40 is greater than this one. So definitely 40 is on the right hand side. Go to right hand side. Is it 40? No, this is 50. So 40 must be on the left hand side of 50. Go on left hand side. This element is found. So we have compared only few elements in a tree and found the result.
So it's left to right. Let's go.
So this is useful for searching an element in less number of comparisons. So this is more like a binary search. Binary search is applied on a single array in a list of elements, but this is upon binary tree.
It's binary search tree. Genius.
So the behavior is similar to binary search.
Genius
So the search time depends on the
words.
height of a tree. We'll learn about search in more detail in other videos. Now let us learn about the properties. First thing, binary search tree will not have duplicates. It will not have duplicates. Now the second one, if we take the in-order traversal of binary search tree, we get the list of elements in sorted order. Let us check. I will perform in-order traversal of this one. Start from root. Move around the boundary. Yes, we have reached the bottom. 10, 15, 20, 30, 40.
In order
50.
is a sorted array.
60.
Brilliant.
Over. So you got the elements in the sorted order. So in order gives sorted order. In order gives sorted order. Then third property. If we have some nodes, then how many different binary search trees can be created for same set of nodes? So number of binary search trees for n nodes. So the third and the last one is number of binary search trees for n nodes, if n nodes are given. So I'll remove this and show you for n nodes how many binary search trees are possible. See here, I have 3 nodes, 10, 20, 30. Then I want to generate binary search tree from those 3 nodes. So what are the different shapes possible? So we know very well that.
Well, is these AVL tree, search tree, fuck, so we have like 3 different trees. Okay, interesting. So BST, where is it used? Shows up all over classical and indirect decision tree models supporting indices and priority. In core computing, BST is a fundamental way to make my dynamic or efficient insert delete log time. Time when balanced, they underpin many higher level structures, symbol trees, lookup tables. Okay. Let's go.
That if we take the in order of a binary search tree, we should get the elements in sorted order, same order. So always it should be sorted order. So if you remember, for the same pre-order, how many trees are possible, we saw it in one of the video. Now for same in order, how many trees are possible? I will draw them, then we will see.
Range
yes,
some of
5 trees are
binaries.
possible.
Okay, give me a second. I need to do this. Given the root of a node of binary search tree and 2 integers, low and high, return the sum of all nodes with the value of inclusive range, low/high. We have the fuck this here, low/high. So I need to give a. How do I do that? I'm pretty sure there's like a way to go about it too. So wait. $700. Fuck this bitch. Allah. You're given a root of a binary tree and an integer value L, integer val. Find the node in the BST that nodes equal to val and return the subtree rooted with the node if such does not exist. Return. Okay. What? You're given in the binary search tree an integer val. Find the node. Okay, I need to find the node. Okay. So def DFS. Okay, and I need to go search this shit. I think so. Maybe not. Maybe I should take this. I need to go. I need to go self.valve. No. Fuck. I need to do it. How do I do it though? Solution. Let's look at solution. Okay, so fuck you, Java solution. Fucking piece of shit. Nigga, show Python. Can you show Python, please? Fine.
Hey everyone, today we are going to solve the LeetCode question search in binary search tree. Okay, so let me explain with this example 7, 5, 10, 2, 6, 8, 15, 12, 20, and the bar equal 15. So this is a very basic question, and it's good practice to understand the binary search tree. So typical binary search tree is like this. So now we have root node with value 7. All values of left side of root node are less than current root value. So 5 to 6, right? All values are less than 7, right? Looks good. And on the other hand, all values of right side of root node are greater than root value. So 10, 8, 15, 12, 20, all values are greater than 7, right? So looks good. And the same rule apply to the all subtree. So for example, this subtree, we have 5 as a root node, and look at the left side, we have 2, and look at the right side, we have 6, right? So left side is less than a root node, and the right side is greater than root node. So looks good. And look at this subtree. In this case, 10 is a root node, and the left side is 8, and the right side is 15, so looks good. And from 15, so this 15, so root node is 15, so that's why 12 should be located on the left side of 15, right? And 20 is greater than 15, so that's why 20 is located on the right side of 15. So looks good. So this is a basic idea. So we have to find 15, right? So start from root node, and so if you know binary search tree, so you already know which way should we go. So we have two choices: go to left side or go to right side. And 15 is a great.
If it is equal, okay. I think I know what to do. If root dot val equal to val return true. If else if root dot val is bigger. Okay, val is bigger than root dot valve. I need to send this shit to the right side. So I'm gonna call the search. So I need to go self dot search this thing. And I need to go root dot left comma val else if I need to return false at the end. It is bigger than this thing. I need to return the root. Okay. No, don't do that. Okay, that should work. Why? Why, baby girl? Why? Maybe. I thought of it for a second. I was like, that doesn't make any sense. Return none? Fucking hell. Bro. Word for word, bar for bar. Okay, I need to return it, for fuck's sake. Okay, maybe. Hey, this is gonna sound revolutionary, but I think this is the one. Pretty sure. Else if, motherfucker. Now that I see it, I don't need it, but fucking hell, bro. Fucking hell. So is this a BST? It's definitely not BST. I'm not convinced this is BST. This is just some BS. I mean, yeah, it is BST, I guess. I've returned false. I mean, there's only like two different options. Let's do this. Shook. Copy all of this shit. This one, I kind of get it. Bro. Why do I return false? Oh, none. If it is none, the loop will like keep going. If it is false, thank you. $700. search in binary search, whatever the fuck. What the fuck? Search. You don't have it in ya, do ya? You don't have it in ya. Okay. No, delete node in BSD. Search. Where is search in BSD? Search in BSD. You're not gonna have that. Delete in BSD. Okay, let's try delete. Delete node. Delete tree level. Insert into. I think I can do that too. It's medium. Fuck. So I need to delete the entire thing, and this one moves here. So the way I would do is, if not root, I need to return. What do I need to return? I need to return none because I want the loop to keep going. So I need to go back and I need to ask, okay, okay, what's going on? I need the value is key. So if root dot val is equal to key, if root dot val if root dot val is equal to return, I need to delete it. How do I delete it? Return. What's the function for deleting? Bro, I know it could be done easier. Stop lying to me. Fuck's sake, it's too complicated. Complicated. Bro, look at how. Bro. Okay. Let's not do this. I just hate this shit. I hate this shit. Delete node and insert into binary tree. Lowest common ancestor. This is BSD. Any AVL? AVL tree? What the fuck is AVL tree? Binary search, lowest common. You're given in a binary tree where all nodes are value are unique. Okay, fine. Easy, yes. Minimum absolute difference in BSD. Range of BSD. What the? Yeah, bro. Canon. Minimum absolute difference. 2 sum 4. Input is a BSD. What the hell? Range of sum. Okay, I think I can do this. You're given a root of a node in a binary search tree and 2 integers low and high. Return the sum of values low and high. Yeah, let's get, okay. So everything in between here. Okay. So 7 plus 10 plus 15 plus 5. No 5. What the hell? So high 6, 6 and 10. Can you not just I don't know 6 and 10? Where is 6? 6 and 10. So it's going to be 6 plus 7 plus 10. I don't understand the question. How could it be? How could it be? I don't understand the question. Let's.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem range sum of binary search tree. So binary search tree, that's not just a normal binary tree, that means it has the sorted property where for every node, everything in the right subtree is going to be greater than that node, everything in the left subtree is going to be less than that node, and the definition is recursive, so it's true for every single node in the tree. I will say that for the most part, it being a binary search tree actually doesn't make the solution any more efficient. You'll see what I mean in just a second. What we want to do is, given this binary search tree, as well as two numbers low and high that form an inclusive range of values. So for this example, we have 7 and 15. We want to get every single node in this tree that is in this range, including the edges 7 and 15. So we have, it looks like 3 elements that satisfy that. Then we want to add all of them together and return the result. So in this case, that would be 32. Now, the first thing that you might think of, given that we have this range, you can think of a binary search tree as a array that is sorted, because that's kind of how I'm this value now each here, which in the worst case can be the height of the tree, which if it's a balanced tree, it can be log n, but in the worst case, recursive function range their case.
So that's like the biggest thing we need to keep in mind, which is it going the left way or the right way? So let's go here, and if not root, return none, maybe. Return false, maybe, I don't know. And I need to check if root dot val is equal to is in the range. So meaning if it's inside, and can I do that? Okay, if it is bigger, if this proposition is true, low and high, I need to, so let me create result. I need to one result dot append result dot append root dot val. Also, I need to return this thing, which I hate. Bro, I need to do this. Low dot. Okay, low. Because it is what else? So let's say 7 is within the thing, and we check. Okay, 10. If is it in? Okay, let's go to the left side. else if the I need to do all of this, and it's keep going on to the left thing. It will go to the right, and let's go right. And I need to, what do I need to do? I don't need to return. I need to return this thing. This should work. Why?
Case if it
Return 0. Okay, whatever. Nigga, what? Why is that even an issue? I don't get it. Like,
it's actually lower than low, then we return self.range sum BST from the right subtree. We're looking for larger values than this because this is too small. Now, if neither of those execute, then we know for sure that this value is in this range from low to high. So let's return self.range sum BST, calling it from the left subtree as well as from the right subtree, adding those together, and also adding to this the current root dot value, because we know this value is definitely within that range. I think this is the whole code, but I do notice that I forgot to pass in low and high, so I'm going to quickly do that. They're not really
no, bro. Range of sum of BST. Let's try this. Broski. I don't think this is tough. Exactly. Can you like stop copying that guy? It's kind of like embarrassing. That's my code. That's exactly my code. You fucking bro, stop stealing my code, man. That's exactly my code. Bro, that's exactly my code. Oh my god. Oh my god. Okay. I need to do it in why, bro? That's exactly my. You don't even need a fucking thing, bro. These guys, bro. These guys steal my code, my ideas, my genius ideas. It's crazy. It doesn't matter. Well, I don't even need a extra function. I need to list.append. Yes, I'm doing that. So I can call it this way. Bro, yeah. Okay, I don't need this maybe. This is the code. Why is this? Oh, thank you. Thank you for that. Fucking hell, self. Um, what? What? So that was my bro. I'm such a genius. Oh my god. Why am I such a genius sometimes? Like, damn. Damn, bro. Damn. I'm such a genius sometimes. Like, damn. Makes you think. It's like, wow. This nigga's a genius. So this logic is infallibly correct in like every regard. I just need to do, okay, fine. Let's do result. Let's do DFS. Let's pass in root. And let's do, if not in root, return false, all of this shit. Bro, why do I know that? It's crazy. First time doing it too. Divine intellect. I'm the best programmer in the world. God gave me divine intellect. So true. Result dot append. Need to append root dot value. And I need to DFS. Yeah, it doesn't really matter if it is sorted or not non-sorted array. It's all the same. I need to call the function. So DFS root and return sum of result. Oh, let's go. This was my idea, so that just means it's better. My idea is just better sometimes. And yeah, thank you, God. Okay, let's go. Let's move on to the next thing to conquer, because the conqueror's blood is in me sometimes. Let's see. Minimum distance between BSD nodes. Okay, given a root binary search tree, return the minimum difference between the values of any two different nodes. Small, 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 small. Minimum difference. This is the smallest. Okay. How am I gonna go about it? I need to go. It's not. Should I do a DFS? I think I need to do min. I need to take a minus absolute minus absolute value of two nodes. How do I do that? Root val. So I need to take the val. If val, okay. Okay. If root dot val minus self dot, I should do that maybe minus. Okay, if the absolute I need to go minus result dot append absolute value of root dot val minus self dot this thing. Does it even work? Not left. Left, maybe. And I need to return the minimum. I don't think it's going to work. Definitely, this is definitely like what's going on. So maybe I should like I don't see left and right. Need to go left. Chick 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 chick. Coming back. What's wrong in this? C sharp. You like stupid or something? I got this solution in C sharp. You're a faggot. You're a dumb nigga. Ooh, this is between. Okay, let's go.
Hey everyone, welcome back, and let's write some more neat code today. So today let's solve the problem minimum distance between BST nodes. So we're given the root of a binary search tree, and that's the first observation that you should make. This is not just a regular binary tree, it is a binary search tree which has the sorted property where for every node, every value in the left subtree is going to be less than that given node. Well, the values are going to be less than that given node, and every value in the right subtree is going to have values that are greater than that given node, and this property is recursive, so it's going to be true for every subtree as well. All we want to do with this binary search tree is return the minimum difference between any two nodes in the tree. That basically means we have to pick two nodes in the tree, take the difference between them. In this case, the difference between 6 and 2 is going to be 4. And then return that difference. And we want to minimize this difference. So maybe we can find an even smaller minimum between 4 and 6. So 6 minus 4 is going to be 2. What is going to give us the smallest minimum? It's going to be between 1 and 2, which is going to equal 1. Or we could even say 3 and 2 gives us that difference, which will be 1. Or we could even say 3 and 4 gives us that for n. We compare to 1 tree on a node traversal, because we're going to take equal to 2. We're going to take the difference, 3 minus 2. It's 1, so it stays the same. Then we're going to end up visiting the 4. We're going to pop all the way back up. Because this is in order traversal, with in order traversal for a tree, we end up doing the entire left subtree, then visit that node, and then do the right subtree, just like we did with this subtree here. But now we're at 4, so we take 4 minus the previous value, which is now going to be equal to 3. So 4 minus 3, that's also going to give us 1. And then finally, the last node in the tree is going to be 6. We're going to take 6 minus 4. That's going to be 2. That's definitely not smaller than our current minimum over here. So overall minimum that we're going to return is going to be 1. And you can see we just had to iterate through the tree once. We had to visit every node once. So the overall time complexity here is O of n. We don't have to compare every pair of nodes, only adjacent pairs. So now let's go ahead and code this up. Like I said, we're going to keep track of a couple variables. One is the previous node, and one is going to be the result we have. Initially, I'm going to set the previous node to null, and I'm going to set the result equal to a really large number. In this case, in Python, you can usually do float of infinity, but since we're trying to minimize the result, it makes sense to set it equal to a very large number. Now, let's actually do our depth first search, and I'm going to define it inside of our outer function because then we don't have to pass these guys in. These will essentially be considered global variables within the DFS. It's a pretty good trick to use with these recursive problems when we need to update some other outside variable. Update the result. We want to minimize it. We're going to set it equal to the minimum of either itself or the current value, the current difference, which we can get by taking the current node's value and subtracting from it the previous node's value. We can only do this if the result is non-null though. After we're done with that, we're going to call DFS on the right subtree, but shouldn't we update the previous pointer before we call DFS on the right subtree? What will be the previous node? Well, it's going to be the current node. So we set previous equal to the current node before we call DFS here. And we expect that after calling DFS on the left subtree, the previous pointer will be updated. So then we can do this. And that's pretty much it. Oh, there's one last thing, and you definitely don't want to forget this, is to declare these variables non-local. Since they are not objects, we have to do this in Python. Otherwise, they'll be considered local variables to this function, and we'll get like using this without assigning it, that type of error. So we want to declare these as non-local if we want to use them within this function, if we want to modify them especially. like reassigning the result and previous. We have to do this. Lastly, we have to actually call our DFS. We'll do that out here, calling it on the root node, and then we're going to go ahead and return the result that was computed within this function. Now let's run the code to make sure that it works. And as you can see, yes, it does, and it's pretty efficient. If this was helpful, please like and subscribe.
Fuck you. Fuck. I need to get the sorted array into a binary tree. So how do I figure out 0 goes on top and not 9 on top? Okay, let's look the boys video.
For 3 nodes, 5 different shapes are possible. So I have taken 5 shapes. Now in each shape, the elements are filled such that if you take the in order, so we get 10, 20, 30 for all these trees. If I change the arrangements of these elements, I will not get the same in order. So each shape can be filled only in one way to get the same in order. So you already know the formula. For 3 nodes, when 5 trees are generated, and for n nodes, how many trees can be generated? So 2n Cn by n plus 1 trees can be generated. Catalan number. So if n nodes are given, various shapes, binary trees can be generated, and that number is 2n Cn by n plus 1. And one more point.
I'm gonna, yeah, why not? So how many types of trees are there? So let me get my pen. So we have AVL, binary search tree. What else? AVL trees. Fuck you, search trees. Why not?
The top. Our next topic is 2-3 trees. So in this video, I'll be discussing about what are 2-3 trees, its properties we will learn, then how to insert or create a 2-3 tree, then deletion, then I'll do analysis. Then at last I can explain you why we need 2-3 trees, what is the use or what is the purpose of 2-3 trees. So let us start with what are 2-3 trees. Introduction to 2-3 trees. 2-3 trees are search trees. Like we have binary search tree. Binary search tree can contain one key
Binary
and
search
2
tree
children.
and this search trees. Search tree. Interesting. Interesting.
Like this, we can have a value here. Topic is AVL.
Let's see what is AVL trees. I really want to know.
Today we're going to learn about AVL trees. AVL trees are a type of self-balancing binary search tree known after its inventors, Adelson-Velsky and Landis. We've covered another self-balancing
Where is AVL used?
binary search tree on this channel, red-black trees. Remember, for these type of trees, during insertion and deletion, we may need to perform fixes to keep the tree height balanced. This guarantees specific time complexities for our operations. Similar to red-black trees, AVL trees have a time complexity of big O of log n for search, insert, and delete. As a reminder, the definition of height is the number of nodes on the longest path from the root to a leaf node. The central property of AVL trees is that for any node, the height of its two subtrees differ by at most 1. We call this the balance factor, which is found by taking the height of the left subtree and subtracting the height of the right subtree. This means that valid values of balance factor are -1, 0, and 1. Let's take a look at an AVL tree. Note that we'll say an empty tree has a height of 0. So leaf nodes have a height of 1. I'll put the height of each node in green. And I'll put the balance factor of each node next to the height in blue. Remember that balance factor is calculated by taking the height of the left subtree minus the height of the right subtree. Let's take a look at 50. Its height is 5 because there are 5 nodes on the path from 50 to 83. To find its balance factor, we take the height of its left child minus the height of its right child. 3 minus 4 is -1. Please pause the video here if you need some time to review this. Here's an example of a tree that is not an AVL tree. As you can see, it has a node with a balance factor greater than 1. Next, let's take a look at how AVL trees compare to red-black trees. In the worst case, AVL trees and red-black trees have identical time complexities for search, insert, and delete, big O of log n. However, for amortized time complexity, red-black trees have a time complexity of big O of 1 for insert and delete. If your application is lookup intensive, AVL trees are more efficient because they are more strictly balanced. That is, the height of an AVL tree is bounded by 1.44 times log base 2 of n, while red-black trees are bounded by 2 times log base 2 of n. Proving these values is outside the scope of this video, but I put links in the description if you want to know more. I'll also link a paper from Ben Pfaff, who used to teach at the computer science department at Stanford, where he concluded that if insertions often occur in a sorted order, AVL trees excel when later accesses tend to be random. Take a look at the paper if you're interested. He compares unbalanced binary search trees, AVL trees, red-black trees, and splay trees. Let's take a look at some code. For our nodes, we'll hold the data in an attribute called key. We maintain pointers to the left and right child, and we also store the node's height, which is set to 1 upon creation. For the tree, we'll keep track of a pointer to the root node.
A binary search tree is only fast when it is balanced. What happens if the binary search tree is not balanced? It is possible for the tree to be a singly linked list to the right. When searching this, it can take up to big O of n time to find the node. We need a way to automatically balance the tree. This is where an AVL tree comes in. An AVL tree uses rotations to keep the binary tree balanced. First, we need to define the height and balance factor. The height at a node is the length of the longest path from that node to a leaf node. The height of the leaf nodes are 0. For example, the height of the root is 3 because the length of the path from the root to the rightmost leaf is 3. Here are all the nodes labeled with their heights. The balance factor of a node is height of the left node minus the height of the right node. Here are all the nodes labeled with their balance factors. Note that for the node with value 20, since there is no right child, we take the height of the right node as -1. A tree is balanced when all its balance factors are either -1, 0, or 1. Let's start with a simple tree with just 2 nodes, 10 and 20. Now, if we insert 30, the tree becomes unbalanced. We can calculate the heights and balance factors for each node. As you can see, the balance factor of the root is -2, which is less than -1. To fix this imbalance, we need to perform a rotation. As you can see, the balance factors are now all between -1 and 1. The rotation we performed is called a left-left rotation. There are 4 types of rotations in an AVL tree. The first one is a left-left rotation. It is used when the tree is heavy on the right side. Here the root has balance factor -2 and the balance factor of the right child is -1, which triggers a left-left rotation. We rotate left. Node 20 becomes the new root, node 10 becomes its left child, and the pointers to the subtrees are updated. After the rotation, the heights and balance factors are within the acceptable range. The second type of rotation is a right-right rotation. It is used when the tree is heavy on the left side. It is just the mirror version of the last type of rotation. Here the root has balance factor 2 and the balance factor of the left child is 1, which triggers a right-right rotation. We rotate right, node 20 becomes the new root, node 30 becomes its right child, and the pointers to the subtrees are updated. After the rotation, the heights and balance factors are all within the acceptable range again. The third type of rotation is a right-left rotation. It is used when the tree configuration is like shown. Here the root has balance factor -2, and the balance factor of the right child is 1, which triggers a right-left rotation. We rotate such that node 20 is brought up to be the new root. Node 30 becomes its right child, and node 10 becomes its left.
Is basically like some Sara type shit, universal balance and whatnot. Makes sense. In order traversal, BSD. Let's do another BSD. Why does this not work? The fuck? Doing all of this bullshit, previous and all of that. Let's give it a try. Let's give it a try.
Everyone. 2, it's 1, so it stays the same.
Let's give it a try. Try. Keep trying. So we have a previous result is equal to none, and float. I'm just like redoing it from infinity, right? And we're going if not root return false, and if previous exists, okay, we need to go to the that is definitely a thing, so I need to go on dfs root if previous exists. I need to check if no, I need to call the thing. Fuck. root dot left, because left is like the smaller values. What am I doing? Do I need to call them?
This case with want to minimize it.
Okay, previous result.
Well, on the left subtree, the previous.
Okay, what is going on? I don't need this. I don't need this. Okay, what is going on? DFS. Result is equal to, oh yeah, makes sense. Minimum of absolute value of one of absolute what? What do I need even? I need absolute. What am I doing? Prev without valve, previous node or a value. So and prev. It's going to be increasing, so it doesn't matter. Okay, root dot valve. I need to go and on the same line, right? Nah. Okay. Prev is equal to node and DFS root dot right. Whoa! What's wrong? What's wrong, bro?
Variables non-local. Since they are not objects, we have to do this in Python. Otherwise, they'll be considered local variables to this function and will
Node. Oh, hell. Okay, maybe go back. Go back. For no reason. Non-local prev. I need to return something. I feel like I need to return.
we'll get like using this signing ahead and return the
Okay. How long have I been streaming? 2 hours. I'm gonna take a break. Does it really matter? Does this really matter? Non-local in Python.
So 2n Cn by n plus 1.
Yeah, I think non-local is really. Fuck, I just wanna beat someone up. Global scope, non-local. Okay, give me a second.
Shortly afterwards, we saw him heading straight towards the mountains, some 70 kilometers away. These penguins are all heading to the open water to the right. But one of them caught our eye, the one in the center. He would neither go towards the feeding grounds at the edge of the ice, nor return to the colony. Shortly afterwards, we saw him heading
Hello. Okay. Hey, hey, too much mocking. Okay, give me a second. I'm back. We're gonna do some BST, BST easies, and AVL. Going according to the plan. Ooh, that looks good.
Sweet.
I said lean with it, rock with it, your finger, I could put a rock in it. I said lean with it, rock with it, your finger, I could put a rock in it.
Let's do some AI. Okay, let's, bro. So trash. Why is everything that this shit creates is so trash? You guys are so trash. Oh my god. Who are these Bomba glass, bro? What the fuck am I looking at? What the fuck am I looking at? In a second, I might start doing what I'm supposed to do.
You should have put that on, because that's good. Let's have a look at it. That looks so bad. Oh, let's see if you can see. Yeah, you look sharp. Oi, yeah. Trim looks good in that. Let's have a look. Yeah, oi, that's edited though. No, why is this Mrs. edited that photo? That shirt is what I got done for worst cover. That's good, mate. Yeah, but that's a nice holiday t-shirt, mate. Not to go out, not for a night out. It was summer. It was summer. No. What was the excuse you wore that?
Okay. Binary search tree. Just get back into it.
So each shape can be filled only in one way to get the same in order. So you already know the formula. For 3 nodes, when 5 trees are generated, and for n nodes, how many trees can be generated? So 2n Cn by n plus 1 trees can be generated. Catalan number. So if n nodes are given, various shapes of binary trees can be generated, and that number is 2n Cn by n plus 1. And one more point we observe, again I repeat the point, in one shape, the key elements can be filled only in one way. If I write 20 here, 10 here, I will not get the same in order. Then let us see how we can represent this binary search tree. Binary search tree is represented using linked representation. If you want, you can use array also, but mostly it is done using linked representation. So I will draw a linked representation for this one. So this is the linked representation of this binary search tree. So that's all. Introduction to binary search tree. We have also learned about its properties. Now next video we'll learn how to search in a binary search tree. Now let us look at searching in a binary search tree. I have an example of binary search tree here. I will show you the procedure by taking some keys. Suppose I want to search for a key value that is 25. Then for searching 25, you can see that 25 is present here. Start from root. Take a temporary pointer on the root of a node. Now let us see the procedure. What are the steps? Wherever t is pointing, check for the data and compare with the key. Key is smaller than the data. So if t is small, move t on left child. The next same thing, repeating step. Wherever t is pointing, check the data and compare with the key. Key is greater than data in this node. So move t on right side. Then again repeat. Check wherever t is pointing. Data, compare. Yes, it is same. So element is found in that particular node. So that's all. Search is very simple. So in how many comparisons I got this element? 1, 2, 3. 3 comparisons I got the element. Now I'll take one more key element. Key is 40. Start from root. Now start the procedure. Compare data with the key. Key is greater than this data. Move t on right side. Then again repeat. Compare key with the data. Key is equal. Matching. Element found. So how many comparisons we found? Just in 2 comparisons I found this. So it means if I'm searching for 30, I'll get it in just 1 comparison. So maximum how many comparisons required for searching? If I'm searching for these elements which are in the...
Give me a second.
Then the maximum comparisons are dependent on the height of a tree. Yes, the time taken for searching depends on height of a tree. So I can say that the time is order of h, where we know well that height of a binary tree can be minimum log n and maximum n. So height can be from log n to n. So we can go for minimum one and say it is log n. So minimum time is log n. So the time taken for searching in a binary search tree is log n. Next, we look at unsuccessful search. See, these 2 searches, the key elements were present in the tree. So this is a successful search. If the key element is not present, then what happens? Let us take a key element, 21. Start searching. Start from root. Compare data with the key. Key is smaller than data. So go on left side. Compare data with the key. Key is greater than this data. So move on right side. Compare key with the data. Key is smaller than this one. So move on the left side. T became null. On the left side of 25 it was null. So T became null. So we have reached the end of binary search tree. So it means the element is not found. Unsuccessful search. So in unsuccessful search also maximum how many comparisons are done? 1, 2, 3. This is null. So we did not do anything. So maximum comparisons are equal to the height of a tree. So height we assume that it is minimum. Right? We don't assume that it is maximum. We assume it is minimum. So it is log n. Next I will write down a recursive procedure for performing search in binary search tree. Function name is rsearch. Recursive search.
Bro, I don't want to study today. Fuck. I want to do backtracking and some chess stuff, but it's like... What is this? Okay, let's go back into it.
Search, which takes pointer to a node, call it as t, and the key element that we want to search. What it will return, I will write at the end. Every time what we have to do, whether that t is null or not null. If it is not null, then we compare. If it is null, means element is not found, and we will stop. So first I will write down, if t is null, I will write down failure condition first. If t is null, then return null, means element is not found. Otherwise what? Compare. If key is equal to t is data, if it is matching, then the key is found. Then return t. So it should return the pointer to a node in which that key is found. Else, if key is less than t is data, if it is on the left hand side, then perform search on the left subtree recursively. So it will call itself recursively r search by passing t's left child and key. This result will be returned. Otherwise, means it's not matching, it's not less, then definitely it is greater. So search in the right subtree, r search in right subtree. So this is a recursive function for searching in a binary search tree. So this is a recursive function for searching in a binary search tree. And if you observe, first it is comparing for the data and the last statement is calling itself. Either this statement or this statement. So if the last statement in a function is a recursive call, then it is called as a tail recursion, right? So it's a tail recursion. Anyway, we have solved enough recursions. You can understand how this is working. I don't have to trace it and show you. So that's it. This takes log n time that is equal to the height of a tree for searching. Now let us look at iterative function or iterative function that is using loop. So search function which takes a pointer to a root node and a key, the key that we want to search. Suppose we want to search for a key 25, then t starts from root. So t is at root. So when we call this function, we'll be passing root to this function. Now what it does? Every time check the data with the key. If key is equal to t's data, if key is equal to t's data, means the data is found. So return t, data is matching. If it is not matching, check if it is less. If it is not matching, check if it is less. If it is less, then go to left side. So else, if key is less than t's data, if so, then move t to left hand side. T will move from left hand side. See, our t is smaller, so it has to move on the left hand side. Otherwise, if the key is greater, then it has to move on the right hand side. In every step, it has to do these things. So else, move t upon right side. So I have already checked the condition for equal and less, otherwise it is greater. So this process I have to repeat. So this should come in a loop. While. Let me trace this once again for the key 25. T is pointing here, that is at root. Then first step, key is equal to data. Is it equal to data? No. Is it less? Key is less? Yes. Move t on left side. Then continue. Again check, is it matching with the data? This 20 and 25, they are not same. Is it less? Key is less, 25 is less than 20? No. Greater, so move on the right hand side. Then continue once again. Now check, is it matching? Yes, matching. Return, it will stop. So key is found. Suppose this was not a 25, this was 26. Then, is it matching with the data? No. Key, is it less than this one? Key is not less, it's greater. So move on the right side. Move on the right side. So right side is null. T is null. Continue. No need to continue. T became null. So it means this repetition we should do as long as T is not null. If T becomes null, then stop. And when you stop, come out of the loop, then say return null. So this return null, it returns null when the key is not found. If the key is found, it will return here. So that's all with the search process. So this is the iterative version of search. So that's all. This is the iterative version of search on a binary search tree. So search time already we have analyzed, so it is log n, height of a tree. So that's all. This is a search procedure for searching in a binary search tree, and it is iterative. Now one thing I would like to show you here, that we saw a recursive function. In a recursive function, it was a tail recursion. Now once we learned that when you convert a recursion into iteration, then you may need stack, right? But here we don't need any stack. This is implemented just using a loop. We don't need any stack.
It's hurting my brain. I need to do, let's look at some LLM concepts. This is oh, I need to do this. Fuck. I have like so much shit I want to do, but I'm constrained.
In this video, I'm going to be building a linear regression model from scratch in Python, so no scikit-learn. In this video, I'm going to be building a linear
In this video, build machine learning and statistical models. However, they would often be built in things like Jupyter Notebooks, which have zero business value. So there needs to be a role that kind of combines the software engineering aspect and the data science aspect. And that's where machine learning engineers sits, like right in the middle. So their job is basically to bring this algorithm to life so it can actually generate tangible business value. Because of this broad skill set, a machine learning engineer is not an entry-level role, and you'll typically need a few years' experience as either a data scientist or software engineer first, and then upskill yourself in the other areas. So to summarize, the main responsibilities of a machine learning engineer is to train, build, and deploy machine learning models. You will need to be well versed in both data science, machine learning, and software engineering. So you need to know things like Python, SQL, AWS, Git, Docker, Kubernetes, Bash, and Z-Shell. So kind of the whole tech stack off from the PyData and also from the software engineering side. And finally, like I said, you need a couple of years experience as either a data scientist or a software engineer first. If you want a better understanding of all the various data and machine learning roles, then I recommend checking out some of my previous videos. The first thing is that someone will have an idea or hypothesis about how they can improve one of our models. Then we check if the
How does it actually work though? 3 blue, 1 brown. I go to this channel whenever I have like nothing to like do, and I want to keep myself entertained for a little. Literally for that. Literally a useless channel.
Last video, I laid out the structure of a neural network. I'll give a quick recap here, just so that it's fresh in our minds, and then I have 2 main goals for this video. The first is to introduce the idea of gradient. Here, we tackle backpropagation, the core algorithm behind how neural networks learn. After a quick recap for where we are, the first thing I'll do is an intuitive walkthrough for what the algorithm is actually doing, without any reference to the formulas. Then, for those of you who do want to dive into the math, the next video goes into the calculus underlying all this. If you watch the last 2 videos, or if you're just jumping in with the appropriate background, you know what a neural network is, and how it feeds forward information. Here we're doing the classic example of recognizing handwritten digits, whose pixel values get fed into the first layer of the network with 784 neurons, and I've been showing a network with 2 hidden layers having just 16 neurons each, and an output layer of 10 neurons, indicating which digit the network is choosing as its answer. I'm also expecting you to understand gradient descent, as described in the last video, and how what we mean by learning is that we want to find which weights and biases minimize a certain cost function. As a quick reminder, for the cost of a single training example, what you do is take the output that the network gives, along with the output that you wanted it to give, and you just add up the squares of the differences between each component. Doing this for all of your tens of thousands of training examples and averaging the results, this gives you the total cost of the network. And as if that's not enough to think about, as described in the last video, the thing that we're looking for is the negative gradient of this cost function, which tells you how you need to change all of the weights and biases, all of these connections, so as to most efficiently decrease the cost. Backpropagation, the topic of this video, is an algorithm for computing that crazy complicated gradient. And the one idea from the last video that I really want you to hold firmly in your mind right now is that because thinking of the gradient vector as a direction in 13,000 dimensions is, to put it lightly, beyond the scope of our imaginations, there's another way you can think about it. The magnitude of each component here is telling you how sensitive the cost function is to each weight and bias. For example, let's say you go through the process I'm about to describe and you compute the negative gradient, and the component associated with the weight on this edge here comes out to be 3.2, while the component associated with this edge here comes out as 0.1. The way you would interpret that is that the cost of the function is 32 times more sensitive to changes in that first weight. So if you were to wiggle that value just a little bit, it's going to cause some change to the cost, and that change is 32 times greater than what the same wiggle to that second weight would give. Personally, when I was first learning about backpropagation, I think the most confusing aspect was just the notation and the index chasing of it all. But once you unwrap what each part of this algorithm is really doing, each individual effect that it's having is actually pretty intuitive. It's just that there's a lot of little adjustments getting layered on top of each other. So I'm going to start things off here with a complete disregard for the notation and just step through those effects that each training example is having on the weights and biases. Because the cost function involves averaging a certain cost per example over all the tens of thousands of training examples, the way that we adjust the weights and biases for a single gradient descent step also depends on every single example. Or rather, in principle it should, but for computational efficiency, we're going to do a little trick later to keep you from needing to hit every single example for every single step. In either case, right now, all we're going to do is focus our attention on one single example, this image of a 2. What effect should this one training example have on how the weights and biases get adjusted? Let's say we're at a point where the network is not well trained yet, so the activations in the output are going to look pretty random, maybe something like 0.5, 0.8, 0.2, on and on. Now we can't directly change those activations, we only have influence on the weights and biases, but it is helpful to keep track of which adjustments we wish should take place to that output layer. And since we want it to classify the image as a 2, we want that third value to get nudged up, while all of the others get nudged down. Moreover, the sizes of these nudges should be proportional to how far away each current value is from its target value. For example, the increase to that number 2 neuron's activation is in a sense more important than the decrease to the number 8 neuron, which is already pretty close to where it should be. So zooming in further, let's focus just on this one neuron, the one whose activation we wish to increase. Remember, that activation is defined as a certain weighted sum of all of the activations in the previous layer, plus a bias, which is all then plugged into something like the sigmoid squishification function, or a ReLU. So there are 3 different avenues that can team up together to help increase that activation. You can increase the bias, you can increase the weights, and you can change the activations from the previous layer. Focusing just on how the weights should be adjusted, notice how the weights actually have differing levels of influence. The connections with the brightest neurons from the preceding layer have the biggest effect, since those weights are multiplied by larger activation values. So if you were to increase one of those weights, it actually has a stronger influence on the ultimate cost function than increasing the weights of connections with dimmer neurons, at least as far as this one training example is concerned. Remember, when we talk about gradient descent, we don't just care about whether each component should get nudged up or down, we care about which ones give you the most bang for your buck. This, by the way, is at least somewhat reminiscent of a theory in neuroscience for how biological networks of neurons learn, Hebbian theory, often summed up in the phrase, neurons that fire together wire together. Here, the biggest increases to weights, the biggest strengthening of connections, happens between neurons which are the most active and the ones which we wish to become more active. In a sense, the neurons that are firing while seeing a 2 get more strongly linked to those firing when thinking about a 2. To be clear, I really am not in a position to make statements one way or another about whether artificial networks of neurons behave anything like biological brains, and this fires together, wire together idea comes with a couple meaningful asterisks. But taken as a very loose analogy, we tackle backpropagation. Anyway, the third way that we can help increase this neuron's activation is by changing all the activations in the previous layer. Namely, if everything connected to that digit 2 neuron with a positive weight got brighter, and if everything connected with a negative weight got dimmer, then that digit 2 neuron would become more active. And similar to the weight changes, you're going to get the most bang for your buck by seeking changes that are proportional to the size of the corresponding weights. Now, of course, we cannot directly influence those activations. We only have control over the weights and biases.
Still very strong in neuroscience and psychology of Hebbian learning. Hebbian learning is when particular neurons are coactive, meaning when they fire together, they tend to strengthen their connections with one another. And it has a number of different underlying cellular and molecular features that we don't have to go into in detail. But for those of you that want to know, I know some of you are hungry for a little bit more neuroscience. This involves things like NMDA receptors. These are receptors. It's a very...
But just as with the last layer, it's helpful to just keep a note of what those desired changes are. But keep in mind, zooming out one step here, this is only what that digit 2 output neuron wants. Remember, we also want all of the other neurons in the last layer to become less active, and each of those other output neurons has its own thoughts about what should happen to that second to last layer. So, the desire of this digit 2 neuron is added together with the desires of all the other output neurons for what should happen to this second to last layer. Again, in proportion to the corresponding weights, and in proportion to how much each of those neurons needs to change. This right here is where the idea of propagating backwards comes in. By adding together all these desired effects, you basically get a list of nudges that you want to happen to the second to last layer. And once you have those, you can recursively apply the same process to the relevant weights and biases that determine those values, repeating the same process I just walked through and moving backwards through the network. And zooming out a bit further, remember that this is all just how a single training example wishes to nudge each one of those weights and biases. If we only listen to what that 2 wanted, the network would ultimately be incentivized just to classify all images as a 2. So what you do is you go through the same backprop routine for every other training example, recording how each of them would like to change the weights and the biases. And you average together those desired changes. This collection here of the averaged nudges to each weight and bias is, loosely speaking, the negative gradient of the cost function referenced in the last video, or at least something proportional to it. I say loosely speaking only because I have yet to get quantitatively precise about those nudges. But if you understood every change that I just referenced, why some are proportionally bigger than others, and how they all need to be added together, you understand the mechanics for what backpropagation is actually doing. By the way, in practice, it takes computers an extremely long time to add up the influence of every single training example, every single gradient descent step. So here's what's commonly done instead. You randomly shuffle your training data and then divide it into a whole bunch of mini batches, let's say each one having 100 training examples. Then you compute a step according to the mini batch. It's not going to be the actual gradient of the cost function, which depends on all of the training data, not this tiny subset. So it's not the most efficient step downhill, but each mini batch does give you a pretty good approximation, and more importantly, it gives you a significant computational speedup. If you were to plot the trajectory of your network under the relevant cost surface, it would be a little more like a drunk man stumbling aimlessly down a hill, but taking quick steps, rather than a carefully calculating man determining the exact downhill direction of each step before taking a very slow and careful step in that direction. This technique is referred to as stochastic gradient descent. There's kind of a lot going on here, so let's just sum it up for ourselves, shall we? Backpropagation is the algorithm for determining how a single training example would like to nudge the weights and biases, not just in terms of whether they should go up or down, but in terms of what relative proportions to those changes cause the most rapid decrease to the cost. A true gradient descent step would involve doing this for all your tens and thousands of training examples and averaging the desired changes that you get. But that's computationally slow, so instead you randomly subdivide the data into these mini batches and compute each step with respect to a mini batch. Repeatedly going through all of the mini batches and making these adjustments, you will converge towards a local minimum of the cost function, which is to say your network is going to end up doing a really good job on the training examples. So with all of that said, every line of code that would go into implementing backprop actually corresponds with something that you have now seen, at least in informal terms. But sometimes knowing what the math does is only half the battle, and just representing the damn thing is where it gets all muddled and confusing. So, for those of you who do want to go deeper, the next video goes through the same ideas that were just presented here, but in terms of the underlying calculus, which should hopefully make it a little more familiar as you see the topic in other resources. Before that, one thing worth emphasizing is that for this algorithm to work, and this goes for all sorts of machine learning beyond just neural networks, you need a lot of training data. In our case, one thing that makes handwritten digits such a nice example is that there exists the MNIST database with so many examples that have been labeled by humans. So a common challenge that those of you working in machine learning will be familiar with is just getting the labeled training data that you actually need, whether that's having people label tens of thousands of images or whatever other data type you might be dealing with. Here, we tackle backpropagation, the core algorithm behind how neural networks learn. The initials GPT stand for Generative Pre-trained Transformer. So that first word is straightforward enough. These are bots that generate new text. Pre-trained refers to how the model went through a process of learning from a massive amount of data, and the prefix insinuates that there's more room to fine-tune it on specific tasks with additional training. But the last word, that's the real key piece. A transformer is a specific kind of neural network, a machine learning model, and it's the core invention underlying the current boom in AI. What I want to do with this video and the following chapters is go through a visually driven explanation for what actually happens inside a transformer. We're going to follow the data that flows through it and go step by step. There are many different kinds of models that you can build using transformers. Some models take in audio and produce a transcript. This sentence comes from a model going the other way around, producing synthetic speech just from text. All those tools that took the world by storm in 2022, like DALL-E and Midjourney, that take in a text description and produce an image, are based on transformers. Even if I can't quite get it to understand what a pie creature is supposed to be, I'm still blown away that this kind of thing is even remotely possible. And the original transformer, introduced in 2017 by Google, was invented for the specific use case of translating text from one
This is 1 year
language into another. But the variant that you and I will focus on, which is the type that underlies tools like ChatGPT, will be a model that's trained to take in a piece of text, maybe even with some surrounding images or sound accompanying it, and produce a prediction for what comes next in the passage. That prediction takes the form of a probability distribution over many different chunks of text that might follow. At first glance, you might think that predicting the next word feels like a very different goal from generating new text. But once you have a prediction model like this, a simple thing you could try to make it generate a longer piece of text is to give it an initial snippet to work with, have it take a random sample from the distribution it just generated, append that sample to the text, and then run the whole process again to make a new prediction based on all the new text, including what it just added. I don't know about you, but it really doesn't feel like this should actually work. In this animation, for example, I'm running GPT-2 on my laptop and having it repeatedly predict and sample the next chunk of text to generate a story based on the seed text. And the story just doesn't actually really make that much sense. But if I swap it out for API calls to GPT-3 instead, which is the same basic model, just much bigger, suddenly, almost magically, we do get a sensible story, one that even seems to infer that a pie creature would live in a land of math and computation. This process here of repeated prediction and sampling is essentially what's happening when you interact with ChatGPT or any of these other large language models and you see them producing one word at a time. In fact, one feature that I would very much enjoy is the ability to see the underlying distribution for each new word that it chooses. Let's kick things off with a very high-level preview of how data flows through a transformer. We will spend much more time motivating and interpreting and expanding on the details of each step, but in broad strokes, when one of these
embedding attention, okay. Embedding attention MLP.
Chatbots generates a given word, here's what's going on under the hood. First, the input is broken up into a bunch of little pieces. These pieces are called tokens, and in the case of text, these tend to be words or little pieces of words or other common character combinations. If images or sound are involved, then tokens could be little patches of that image or little chunks of that sound. Each one of these tokens is then associated with a vector, meaning some list of numbers, which is meant to somehow encode the meaning of that piece. If you think of these vectors as giving coordinates in some very high-dimensional space, words with similar meanings tend to land on vectors that are close to each other in that space. This sequence of vectors then passes through an operation that's known as an attention block, and this allows the vectors to talk to each other and pass information back and forth to update their values. For example, the meaning of the word model in the phrase a machine learning model is different from its meaning in the phrase a fashion model. The attention block is what's responsible for figuring out which words in the context are relevant to updating the meanings of which other words, and how exactly those meanings should be updated. And again, whenever I use the word meaning, this is somehow entirely encoded in the entries of those vectors. After that, these vectors pass through a different kind of operation, and depending on the source that you're reading, this will be referred to as a multi-layer perceptron or maybe a feed-forward layer. And here, the vectors don't talk to each other. They all go through the same operation in parallel. And while this block is a little bit harder to interpret, later on we'll talk about how the step is a little bit like asking a long list of questions about each vector, and then updating them based on the answers to those questions. All of the operations in both of these blocks look like a giant pile of matrix multiplications, and our primary job is going to be to understand how to read the underlying matrices. I'm glossing over some details about some normalization steps that happen in between, but this is, after all, a high-level preview. After that, the process essentially repeats. You go back and forth between attention blocks and multi-layer perceptron blocks, until at the very end, the hope is that all of the essential meaning of the passage has somehow been baked into the very last vector in the sequence. We then perform a certain operation on that last vector that produces a probability distribution over all possible tokens, all possible little chunks of text that might come next. And like I said, once you have a tool that predicts what comes next given a snippet of text, you can feed it a little bit of seed text and have it repeatedly play this game of predicting what comes next, sampling from the distribution, appending it, and then repeating over and over. Some of you in the know may remember how, long before ChatGPT came into the scene, this is what early demos of GPT-3 looked like. You would have it autocomplete stories and essays based on an initial snippet. To make a tool like this into a chatbot, the easiest starting point is to have a little bit of text that establishes the setting of a user interacting with a helpful AI assistant, what you would call the system prompt, and then you would use the user's initial question or prompt as the first bit of dialogue, and then you have it start predicting what such a helpful AI assistant would say in response. There is more to say about an added step of training that's required to make this work well, but at a high level, this is the general idea. In this chapter, you and I are going to expand on the details of what happens at the very beginning of the network, at the very end of the network, and I also want to spend a lot of time reviewing some important bits of background knowledge, things that would have been second nature to any machine learning engineer by the time transformers came around. If you're comfortable with that background knowledge and a little impatient, you could probably feel free to skip to the next chapter, which is going to focus on the attention blocks, generally considered the heart of the transformer. After that, I want to talk more about these multi-layer perceptron blocks, how training works, and a number of other details that will have been skipped up to that point. For broader context, these videos are additions to a mini-series about deep learning. And it's okay if you haven't watched the previous ones, I think you can do it out of order. But before diving into transformers specifically, I do think it's worth making sure that we're on the same page about the basic premise and structure of deep learning. At the risk of stating the obvious, this is one approach to machine learning, which describes any model where you're using data to somehow determine how a model behaves. What I mean by that is, let's say you want a function that takes in an image and it produces a label describing it, or our example of predicting the next word given a passage of text, or any other task that seems to require some element of intuition and pattern recognition. We almost take this for granted these days, but the idea with machine learning is that rather than trying to explicitly define a procedure for how to do that task in code, which is what people would have done in the earliest days of AI, instead, you set up a very flexible structure with tunable parameters, like a bunch of knobs and dials, and then, somehow, you use many examples of what the output should look like for a given input to tweak and tune the values of those parameters to mimic this behavior. For example, maybe the simplest form of machine learning is linear regression, where your inputs and your outputs are each single numbers, something like the square footage of a house and its price. And what you want is to find a line of best fit through this data, to predict future house prices. That line is described by two continuous parameters, say the slope and the y-intercept, and the goal of linear regression is to determine those parameters to closely match the data. Needless to say, deep learning models get much more complicated. GPT-3, for example, has not 2, but 175 billion parameters. But here's the thing, it's not a given that you can create some giant model with a huge number of parameters without it either grossly overfitting the training data or being completely intractable to train. Deep learning describes a class of models that in the last couple decades have proven to scale remarkably well. What unifies them is that they all use the same training algorithm. It's called backpropagation. We talked about it in previous chapters. And the context that I want you to have as we go in is that in order for this training algorithm to work well at scale, these models have to follow a certain specific format. And if you know this format going in, it helps to explain many of the choices for how a transformer processes language, which otherwise run the risk of feeling kind of arbitrary. First, whatever kind of model you're making, the input has to be
Nigga, is deep learning? I thought it was neural networks. Deep learning. Bro, why did you... Okay. Neural networks and deep learning are the same thing. Now,
The goal is for you to come away.
I've been a huge advocate of self-learning ever since high school, and to this day, as I continue on in the university, I still rely mostly on what I teach myself. I strongly believe that proper self-studying is the absolute tier 1 skill, the importance of which cannot be overestimated. But when it comes to teaching yourself, be it a high school class or a data analysis technique that you need for your postgraduate research, it's a slippery slope. There is a lot of stuff you can do wrong that would lower the efficiency of time you put into that. In this video, I will talk about some of the most fundamental pillars behind any successful self-learning journey that I wish I knew sooner. My name is Artem. I'm a computational neuroscience student and researcher. Here we talk about the brain, both the theory of how it works under the hood, as well as practice of how to study and learn more effectively. If you're interested, consider subscribing to the channel not to miss anything. This video is sponsored by Shortform. Have you ever decided to read more, but got lost in the variety of books, not knowing which one is worth your time, or wanting to quickly refresh your memory about a particular book that you read a while ago? Well, Shortform solves both of those problems. Author of the book describes ultralearning as an act of deliberate, self-paced learning of something you're passionate about, with extreme focus, commitment, and immersion into the topic, with direct application of knowledge. Now, there is a lot to unpack in this definition. In fact, Young distinguishes 9 core principles behind any successful self-learning endeavor. You can read about all of them in exclusive detail in the book. In this video, I decided to make an emphasis on only 3 of those principles, the ones that were most helpful and most eye-opening, at least to me. So let's start with meta-learning. To explain the concept of meta-learning, I really like the following analogy. Imagine you're planning to go on quite a dangerous trip in the mountains. Now, you wouldn't just grab random items, stuff them into your pockets, and walk out into the sunset. Instead, you need to thoroughly plan where you will go, examine the trails, read the weather forecast, and decide what to pack with you. And similarly, with intellectual journeys, when you decide to embark on a self-learning project, for example, teaching yourself how to code, you shouldn't just open the first random website or textbook you see and commit to it. Instead, before actually sitting down to learn something, you need to do what's called a meta-learning research. Meta-learning is learning how to properly learn a particular subject. It's about understanding how knowledge in this field is structured and how it should be approached. There are 3 most important questions that you need to answer for yourself: why, what, and how, to enhance the learning process and its results. It's vitally important to truly understand why you want a particular subject and in which context this knowledge will be later applied. For example, let's say you want to learn linear algebra. If you are a computer programmer, you'll probably want to make more emphasis on computational and applicational aspects of it, and not stress too much about the rigorous proofs of the theorems and abstract concepts like the axioms of vector spaces. If you are a pure mathematician, however, the aforementioned approach will be flipped. You can figure this out by Googling the subject of your interest along with your end goal. For example, linear algebra for computer science or statistics for neuroscientists. It's also a great idea to ask the people who already achieved your end goal about their opinion on this. Next, you need to make yourself familiar with what you will be paying attention during your intellectual endeavor. Research the subject, its main definitions, see what comes up again and again. For example, it's a great practice to skim through tables of contents of different resources. What's essential will be in every single textbook, while less important things will be seen less frequently. Another good tip is to play around with Wikipedia. Go to the starting page of a big topic and begin reading. It doesn't matter if you encounter words and formulas you don't understand. We're not trying to learn the content of the subject itself, only what central ideas it consists of. Click on hyperlinks and see how the concepts relate to each other and which definitions and theorems seem to be foundational. Once you can roughly orient yourself around the subject, it's time to determine how you will go about learning. It's about the particular resources you will use. If this is a textbook type of subject, for example chemistry or math, do an internet search which textbooks are recommended for self-studying, or use the existing university curriculum on websites like MIT OCW. If this is more of a skill like coding, search what internet resources and platforms people recommend. Don't underestimate the importance of meta-learning. This is a crucial step and it will pay back in the future. Now, once you're done with meta-learning research, it's time to get your hands dirty. And probably the most important thing that can increase the quality of your learning is proper focus. In fact, focus is so important that I have 2 separate videos dedicated to that topic. But in short, be aware that there is a physiological reason why you can't multitask. Every time you switch attention to something else, even if it's something seemingly quick, like checking your Twitter after every paragraph you read, you literally lose cognitive momentum. That's why it's vitally important to eliminate all sorts of distractions that can potentially hijack your cognitive resources. If you want to take your learning to the next level, you should acquire knowledge in the same context as it will be later applied. And here's what it means. Let's say you want to learn Python for data analysis. The absolute best way to learn is to code as much as possible, playing around with open data sets, doing practice problems from the web, visualizing the data, etc. But it might feel much more comfortable not to do any of this dirty work and just endlessly consume YouTube videos and seminars on this topic without writing a single line of code. This gives you an illusion of moving towards your goal, but in the long
Yeah,
run,
yeah.
this hardly gives any results if you want to get stuff done. And this is the problem, that after years of formal education, we get so used to the abstract, idealized problems that pursuing real-life applications of this very knowledge makes us uncomfortable. It happened to me during my sophomore year in the university when we had our statistics class. I absolutely hated all of those statistical tests because it seemed too abstract and not motivated at all. Of course, somewhere in the back of my mind, I knew that the day would come and this would be useful, but at the moment, I couldn't just grasp all of those assumptions, parametric versus non-parametric, ANOVA, and other stuff. But almost a year later, when I became a part of a research group, my supervisor told me to check the significance of the results we acquired. Now, at the time, I didn't remember anything from our statistics class, so I had to research the hypothesis testing on my own, almost from scratch. But this time, it was different. Notice, because I had a concrete problem I was motivated to solve, the process of learning the required knowledge was A, much more enjoyable, and B, drastically more efficient. Of course, you don't always have the lab to motivate you on a self-learning journey. Here's a couple of strategies for you to try in this case. 1. Personal projects. When learning how to code or how to do graphics design, don't phrase your goal in a way, I want to learn X. It's a great intrinsic long-term motivation, but it's not actionable. Instead, assign yourself a project that you want to complete. For example, I want to create a Python script for plotting fractals, or I will make this animation short. 2. Immersion. Environment you're in can drastically affect your learning. This is why universities, despite the obvious problems, can in some aspects be useful. Because when you're part of this community and you learn as a part of a group, this kind of interaction pushes you forward. So, even when you are on a self-studying quest, it's a great idea to immerse yourself into the environment where your target skill is practiced and routinely constantly applied. For example, when learning a foreign language, you can join these kind of clubs where people meet in places like libraries and coffee shops and practice the target language together. To sharpen your skill of public speaking, there are these discussion clubs as well. 3. Simulation. When you are learning in preparation for something, and that knowledge will be later applied in well-defined, specific circumstances, it's a great idea to replicate them, to prepare in advance. For example, when I was preparing for my TOEFL exam, I did these practice tests in a nice and cozy environment. I was sitting at home, drinking tea and listening to lo-fi music. And I felt pretty confident when walking to the actual exam. But during the test, the experience was drastically different. I was in a single room with a lot of people making all sorts of different noises, and in addition to that, I got super stressed by this huge timer in the middle of the screen that shows you how much time you have left. Now, when I go to my next TOEFL test, I will try to prepare for that environment in advance, or at least get used to the timer. And it's a good practice in general. You can study for a test in the same room, empty classroom, where it will be held. Such preparation, even though it might seem weird at the beginning, actually helps your brain to transfer knowledge and skills between two different contexts. Drill. This is the strategy that nicely complements directness. In fact, they should go hand in hand, alternating each other. You see, while directness gives you basically the big picture, the entire context of how the knowledge will be later applied, drill is when you pick specific points and work on them in isolation. These specific points are usually the bottlenecks, specific aspects that you feel.
Yeah. Kind of see it.
What do nearly all machine learning systems have in common? From GPT and Midjourney to AlphaFold and various models of the brain. Despite being designed to solve different problems, having completely different architectures and being trained on different data, there is something that unites all of them. A single algorithm that runs under the hood of the training procedures in all of those cases. This algorithm, called backpropagation, is the foundation of the entire field of machine learning, although its details are often overlooked. Surprisingly, what enables artificial networks to learn is also what makes them fundamentally different from the brain and incompatible with biology. This video is the first in a two-part series. Today, we will explore the concept of backpropagation in artificial systems, and develop an intuitive understanding of what it is, why it works, and how you could have developed it from scratch yourself. In the next video, we will focus on synaptic plasticity, enabling learning in biological brains, and discuss whether backpropagation is biologically relevant, and if not, what kind of algorithms the brain may be using instead. If you're interested, stay tuned. Despite its transformative impact, it's hard to say who invented backpropagation in the first place, as certain concepts can be traced back to Leibniz in 17th century. However, it is believed that the first modern formulation of the algorithm, still in use today, was published by Seppo Lindenmaa in his master's thesis in 1970, although he did not reference any neural networks explicitly. Another significant milestone occurred in 1986 when David Rumelhart, Geoffrey Hinton, and Ronald Williams published a paper titled Learning Representations by Backpropagating Errors. They applied the backpropagation algorithm to multilayer perceptrons, a type of a neural network, and demonstrated for the first time that training with backpropagation enables the network to successfully solve problems and develop meaningful representations at the hidden neuron level, capturing important regularities in the task. As the field progressed, researchers scaled up these models significantly and introduced various architectures, but the fundamental principles of training remained largely unchanged. To gain a comprehensive understanding of what exactly it means to train a network, let's try to build the concept of backpropagation from the ground up. Consider the following problem. Suppose you have collected a set of points xy on the plane, and you want to describe their relationship. To achieve this, you need to fit a curve y of x that best represents the data. Since there are infinitely many possible functions, we need to make some assumptions. For instance, let's assume we want to find a smooth approximation of the data using a polynomial of degree 5. That means that the resulting curve we're looking for will be a combination of a constant term, a polynomial of degree 0, a straight line, a parabola, and so on up to a power of 5, each weighted by specific coefficients. In other words, the equation for the curve is as follows, where each k is some arbitrary real number. Our job then becomes finding the configuration of k0 through k5, which leads to the best fitting curve. To make the problem totally unambiguous, we need to agree on what the best curve even means. While you can just visually inspect the data points and estimate whether a given curve captures the pattern or not, this approach is highly subjective and impractical when dealing with large datasets. Instead, we need an objective measurement, a numerical value that quantifies the quality of a fit. One popular method is to measure the square distance between data points and the fitted curve. A high value suggests that the data points are significantly far from the curve, indicating a poor approximation. Conversely, low values indicate a better fit, as the curve closely aligns with the data points. This measurement is commonly referred to as a loss, and the objective is to minimize it. Now notice that for fixed data, this distance, the value of the loss, depends only on the defining characteristics of the curve, in our case, the coefficients from k0 through k5. This means that it is effectively a function of parameters, so people usually refer to it as a loss function. It's important not to confuse two different functions we are implicitly dealing with here. The first one is the function y of x, which has one input number and one output number, and defines the curve itself. It has this polynomial form, given by k's. There are infinitely many such functions, and we would like to find the best one. To achieve this, we introduce a loss function, which instead has 6 inputs, numbers k0 through k5. And for each configuration, it constructs the corresponding curve y, calculates the distance between observed data points and the curve, and outputs a single number, the particular value of the loss. Our job then becomes finding the configuration of k's that yields a minimum loss, or minimizing the loss function with respect to the coefficients. Then, plugging these optimal k's into the general equation for the curve will give us
Hey guys, welcome back to the channel. So this channel, Everyday Data Science, is all about trying to learn the different concepts and learning data science by practicing a lot of questions. From this video, us the best curve describing the data. Alright, great. But how do we find
A generic process I recommend for people to prepare interview could be summarized into 3 steps. The first step is to go through.
Hey, I'm Eliza with Springboard. I'm
for my grad school. Why I chose data science? Because I really enjoy coding and also critical thinking. So I feel like if data science is like a perfect position for combining engineering and data analytics together.
Can you tell me a little bit about the interview process for a data scientist? Are there generally a lot of rounds or phone screens?
The general interview process is like phone screen conducted by the recruiter, technical interview conducted by either hire manager, engineers, or senior member, data scientists in the team. And then after these 2 rounds, our candidate is invited to on-site at the company to meet 4 to 6 people in 1 day.
Right. That's a lot of people.
Yeah. And also like during the on-site interview, some of the interviewers are engineers, some of the interviewers are product manager. The candidate absolutely will meet some data scientists and data science manager at the on-site interview.
When you're in the interview, what are some common questions that you'll get asked as a data scientist?
I feel like it really depends on a team. The data scientist position can be categorized. Number 1 is the more data engineering focus. And the second type is like product data science. The third one will be like platform-based data science. During the data science interview process, I see 3 categories. Most common question. Number 1 is for data analysis. Candidate might need to answer the question with the coding language. It can be, how can you count the number of users in this table? How can you join these 2 tables together? A candidate can use SQL, SQL, or R to finish this question. Second type of question a candidate might need to answer is about statistical modeling. So for example, what kind of test a data scientist should use for binomial metrics? So this is about statistical modeling. And then the third one is very common in product data scientists. Interview question is like how to define the success of metrics. So let's say you have an online shopping website and you want to grow your website to attract more traffic. Then how can you quantify this question and figure out the best metrics to measure the new customer to your website?
So in your experience, what's the best way to prepare for an interview?
A generic process I recommend for people to prepare interview could be summarized into 3 steps. The first step is to go through the basic concept of statistical modeling. I saw some candidates who are really strong in understanding the mathematics part, but they forgot what they want to say during the interview. So it's always good to go through the basic concept of statistical modeling. The second step of preparing the interview is to know the product of the company you are going to interview for. So let's say you are going to interview for a position of an online marketing company. It's a good idea for a candidate to understand what's the general metrics of online marketing. The third one is always helpful to practice coding before the interview. So the candidate can look for like coding question online and think about how he or she can answer like SQL and Python questions.
So say you're starting out as a data scientist. What's something that you should focus on learning as you're just starting out?
As a new data scientist who just graduate from school, find a mentor in the company, because like different company has like different product. It's always helpful to have a senior member to help the data scientist to learn about the metrics of success the company care for.
When you get a mentor or when you find a mentor, what do you hope to learn from them when you're starting out?
A data scientist who graduate from college can learn about like presentation skill and stakeholder management skill from their mentor, because these are two things we cannot learn from school. So let's say you have a presentation you want to deliver, you can ask your mentor to give advice to your presentation and your slides that you need to improve.
What's the general career trajectory for a data scientist?
I saw two directions after people grow for many years. The first direction is staying in data scientist, individual contributor track. So the person can be a staff data scientist or principal data scientist in the company and doing very in-depth research work. Another direction can be a data science manager. A data science manager might become like a data science director in the future, and they are going to lead a big data science project for a specific product in the company.
Do you have any tips for someone who's trying to break into the data science industry?
If a person who work for other industry and want to switch to data science, I would recommend they should remember they always have their strengths in their background. So let's say a person who worked for banking before, there's like data science team who focus on finance. So always connect your past project with the available data science position in the market is a good thing.
How can someone be successful in the data science industry with just a bachelor's degree or with no degree at all?
I saw data scientists with bachelor's degree very successful as well. So they, with like only bachelor's degree, some of the data scientists are really strong in coding. Their coding skill in Python and R and Scala are almost like as good as engineers. Another direction for data scientists with bachelor's degree is continue to develop your product sense, because like different company, their product is very unique, and if you can become the expert in the product in your own company, whether or not you have a bachelor's degree doesn't matter. Your knowledge in this product cannot be replaced by academic achievement.
I think that's all the questions we have for today. Thank you so much for joining us. It's been really fun talking to you.
Thank you for inviting me.
Thank you so much for watching. If you have any questions you'd like us to ask data scientists in the future,
This year has been another insane year for AI progress, and I think there's no better way to recap this year by going through the top 10 most cited AI research papers of
becomes finding the configuration of Ks that yields a minimum loss, or minimizing the loss function with respect to the coefficients. Then, plugging these optimal Ks into the general equation for the curve will give us the best curve describing the data. Alright, great, but how do we find this magic configuration of Ks that minimizes the loss? Well, we might need some help. Let's build a machine called CurveFitter 6000, designed to simplify manual calculation.
Okay, I'm back. I'm back. I'm back. So I'm gonna do. I want to do backtracking so badly, but the issue is, if I just jump into backtracking, I think I might be a little clueless for. Okay. Okay, let's do this. Hopefully, it doesn't smell bad. But anyways, okay, let me try to. I need 2 books. Oh no. So on this book, I have every SaaS product that I want to make. On the back of the book, I'm not even gonna do that. Fuck no. Ooh, yes. Okay. Is my audio working? Okay, let's learn some ML concepts and try to be the GOAT. That's why he's the GOAT. The GOAT. Okay, minimum local. Okay, let's see. Do I want to do AI right now? Probably not. There's a lot of ML projects that I want to do. Let's take Notion. I want to do a Tinder project where I get some Tinder data and I see. I mean, everything is done already. Statistical analysis, bro. I don't know statistics. I'm not aware of the data set though. Where do I find the data set? Kaggle should be in the Kaggle. Let's see, Kaggle. Match rate, dating app, and COVID image times on Tinder. Great notebooks about dating. Okay. Dating. Let's collect some data. Data sets. Let's give me some data sets, bro. Patient shown, synthetic source sales data. Ooh, this one. Seaborn? The fuck is Seaborn? GNN, oh, yikes. Bernoulli, who's Bernoulli? I forgot. Seaborn is easier than Matlock. Yeah, I'm not doing Seaborn, bro. I'm not doing Seaborn, genuinely, no. Load data. Okay.
In this part of Stanford CS224.
Okay, bro, shut the fuck up. Shut the fuck up. I wanna... Fuck you. Correlation, heat map, time patterns. It's just a computer way to like represent what's going on. So, how do I? AQI distribution. Okay, let's give this a shot. Style. Fuck no, I'm not doing this. I'm a white man, bro. How to style? Fuck. VS Code. It's just binary search. Let's see. Come on. Fucking bitch. I'm so big. Temporary running file. Your code doesn't work. Visualization. What? Python was not run without argument to install Microsoft on disable settings app. App execution analysis. Or disable this shortcut. What shortcut? I need to download Python. Bro, I don't know my password. What the fuck? Why do you guys have to kill me like this? I don't know my password. I just want to code, bro. Don't want to do none of this shit. Genuinely don't want to do none of this shit. What even is the point? Oh my god. fuck you. Thank you. Whew. Is it going to take long? No. So what's the difference between the versions?
Managing multiple Python versions on your system can be a massive pain. That's why in many of my tutorials you'll see me using a tool called PyEnv. This sucker is amazing. You can install multiple Python versions, switch between them with ease. It's my favorite. So in this video, I'm going to show you how to install it, how to use it, a few of the bells and whistles, get your coffee ready. Let's go.
Why is he like? I know he's like one of the top dogs. But why is he kind of zesty? You could be a top dog in programming and not be zesty. Always have to make it zesty, man. These guys. These network engineers. Literally, literally is one of the okay. Let's try importing this piece of shit. Okay, don't need it. It's backtracking. But a good thing is I know some Hindi. If it wasn't for me knowing Hindi, it's like done.
Hey guys, welcome back to the channel. So this channel, Everyday Data Science, is all about trying to learn the different concepts in non-data science by practicing a lot of questions. From this video, I'm going to start a new series where I'm going to solve questions from from StrataScratch. I recently found out about this website called StrataScratch, and I was really impressed because it has a lot of great questions, and not only the coding part, non-coding, data projects, etc., which we will be doing as we proceed further. And the great thing about this is that you can solve the same question using Python, SQL, PostgreSQL, etc., right? So it will be helpful to understand the connection between like how can you do a certain thing in Python and you can do the same thing in MySQL and vice versa. The lead code series will still continue to come. I'm not abandoning that because I have completed 150 questions in lead code. There are around 50-55 questions that are left, so that series will keep continuing. But
it is equipped with 6 adjustable knobs for K0 through K5, which we can freely turn. To begin, we
look at all this math and code you need to understand to learn machine learning. It can be very hard. For me at least, it was as well, until I learned these 5 secrets, which honestly aren't even secrets, but no one really teaches you them, although everyone should know them. I mean, I spent the last 3.5 years studying machine learning, and it took me way too long to learn these secrets on my own. So let me reveal them to you so that you don't have to struggle for that long. You're thinking of math the wrong way around, which already sets you up for failure at the very beginning. But isn't your fault. Back when I started learning machine learning, some of my professors would simply throw a formula on screen and tell us, this is the loss function for a decision tree. And that was it. I and most other peers were confused and simply stared at the formula and were waiting for a magical aha moment where the formula made sense. I was always asking myself how those smart scientists could understand math so well they could develop new algorithms and just think in the language of math. Until I realized I was thinking the wrong way around. I was focusing too much on the actual mathematical formulas in the realm of math, instead of taking a step back and thinking like a scientist. I mean, I was literally looking at a formula and trying to understand the formula as a whole, which for me now, after learning the secret, just doesn't make any sense anymore. Don't think of math like something abstract and make it then human interpretable. You need to realize that you need to think the other way around. Think of the idea a human had, understand it, and then think of how to translate it into the language of math. This perhaps sounds very confusing, but math is not a standalone language in which people think. Scientists think just like you and me, in natural language. They just know how to translate their ideas into the formalisms of math, which then allows them to be implemented and then further developed using the rules of math. As mentioned, I was always looking at a formula as a whole, but each component of a formula is just a component of this human idea. For example, a sum or a product are literally just a for loop that can have some conditions that are literally equivalent to an if-else statement in code. Of course, this is easier said than done, and to understand a mathematical concept using human ideas requires someone to actually properly teach you these human ideas and how to translate them step by step. But in my experience, there are 2 scenarios. 1, the teacher does that already, but you don't understand he does it because you were never explicitly taught to think that way. Or 2, the teacher does really only look at the formulas and derivations. In that case, you need to try to figure out the original human idea yourself by, for example, looking it up online. But the good thing is, you now know it is not your fault, and there is an intuitive understanding to the math that you can find. Math is just the formalization of a human idea. Very few people actually think in the language of math. It's just a tool. But when it comes to every intermediate derivation step, then you often actually think in the language of math, which is very difficult, unless you know the next secret. This secret literally changed the way I look at scary math derivations like this one. Again, jumping back in time to when I watched a lecture at college, my professor would explain the intuitive idea of an ML algorithm, show the translation into the language of math, and then show us where we want the formula to end up to make it more efficient or simply actually work as an algorithm that can be implemented. But at some point, he would go off on a derivation spree, writing out one step after the other, and expected us to understand why he did what he did. Everyone was confused and, of course, scared and annoyed. But these derivations are simpler than you might think. Not easy, but much simpler to execute after learning this one secret. I realized each step was simply applying one specific rule or definition. I realized that, up to a certain degree, these mathematical derivations or transformations just require you to have a list of rules and tricks you need to collect that you can then simply apply. During the lectures, for each step I see, I would explicitly look for the rule and definition they used and write that down on my list. When solving or reading math derivations on my own, for homework assignments or during an exam, in most cases, I would literally just do some sort of pattern matching. I would look at where I currently am, go down my list of rules and definitions, and apply what fits the pattern. Of course, some patterns, rules, and definitions are harder to spot than others, but after doing this, and learn to recognize when you can apply which rule, which means practice, practice, practice. But math is, of course, far from all there is to ML. Coding is also a very challenging skill. Learning the basics of Python and then an ML library like PyTorch is really cool and fun. You simply follow a tutorial online and have a really steep learning curve. You follow a recipe of steps and implement a lot of code. You really see and feel the progress you are making. But then, when you want to go further and learn to implement actual algorithms or ML pipelines on your own, you hit a wall. All of a sudden, you sit on one annoying problem for several hours, have written perhaps 5 lines of code, and you think you are not making any progress. This is very, very frustrating, and is the point where a lot of people determine coding is really hard and that they will never be able to really learn to code. Writing 5 lines of code in 3 hours, how pathetic. I mean, I always thought I was so stupid for writing code that never worked until I debugged it for hours. This can get so bad that you don't even want to start coding because you know it will fail. But that is simply the wrong way to think. Actually writing code for 1 hour will very likely mean, let's say, 3 hours of debugging. Once I learned that this is what it really means to be coding, I all of a sudden felt so relieved and just not stupid anymore. Coding ML models didn't feel impossible and hard anymore because I was doing exactly what was normal and expected. And nowadays there are amazing tools that I can't live without, like GitHub Copilot, that can generate code for you and explain code for you. But there's so much that you simply learn through your own experience or the experience of others. That's why I have a completely free weekly newsletter where I share things on your own, step by step. There are 2 cases where you will need to understand complex code. The first one is when building on top of an existing repository. I remember when I started working on my first larger project where I built on top of an existing code base. It was so much code, I literally had no idea where to start. Just like in the previous secret, I again felt like learning to read code was as impossible as writing code. All those tutorials and smaller personal projects didn't prepare me for this much code. I tried reading each source file and started to write code as soon as possible into places I thought made sense. But that, unsurprisingly, led to a lot of headaches and wasting time writing code that was destined to fail. I had to learn the hard way that there is a very simple strategy to understanding large code bases. I wish someone would have simply told me once how to approach a challenge like this. With most large ML repositories, you have a train.py and an eval.py file. Those should always be the starting point. I find those files, set a breakpoint in the beginning, and start stepping through the code. Consider poor AI skills, expertise, or knowledge as the top reason blocking successful AI adoption, according to an IBM study from 2022. Why do you think people fail learning ML and fall into the category of people with poor AI skills? Is it because it is hard? Yes, but it was also hard for every person who has now mastered it. People fail to master ML because they stop learning machine learning too early and give up. And why do people give up? Because they have false expectations and don't enjoy the process of learning. They think mastering ML is hard because they didn't learn ML in a few weeks, or because they didn't understand a video explaining an ML concept the first time, they will never understand it. I took my first introductory AI college course about 3.5 years ago. After that semester, I took my first real ML course, along with working on my first ML projects. After that semester, I continued with my first deep learning courses and continued working on projects and reading a lot of papers. I definitely didn't understand everything the first time, but I knew that was normal. Over time, I learned the secrets mentioned before, and that somewhat mastering ML takes time. I failed my first ML interviews for internships at Amazon, Neuro, and Google DeepMind. But now I'm working with an ex-Meta professor and collaborating with a Google DeepMind researcher. It takes time. Period. This is not a skill you learn over a weekend. The 10,000 hour rule applies here as well. If you spend 10,000 hours on a specific skill, you will master it. I'm absolutely not trying to discourage you, rather the opposite.
Okay. Okay, I need to max out. Ah, fuck. So much shit to do. Like, so much shit I can go from. It's crazy. Okay, this should work now. Fuck you. Okay, it works. What is AQI?
If you're like me, you probably barely survived math class back in high school or college. But the irony is that we ended up in a field where math is kind of important. Sure, it might not feel like it when you are styling web apps or performing CRUD operations on a database, but entire fields of programming, ranging from game development to machine learning, are built on top of vectors, matrices, and transformations. This is where linear algebra comes in. And, believe it or not, despite the fact that you are probably still having nightmares where you are naked in front of your math teacher, linear algebra is actually really easy to understand. Let me show you. Let's say you have a bunch of nickels and pennies, and you want to know how many of each you need to have 23 cents. Of course, to get to the total, you need to sum up an exact number of nickels with an exact number of pennies. Luckily for us, this is pretty easy to solve. You could divide 23 by 5 and see that you couldn't use more than 4 nickels, and we'll use 3 pennies to fill in the rest. Of course, we could at any time replace a nickel with 5 more pennies, and this is also a valid solution. Following the same path, we can convert more nickels into pennies, and if we want to get fancy, we could technically have a negative number of nickels and compensate with more pennies. So we got variables, constraints, and a bunch of possible solutions that all satisfy the same rule. In mathematical terms, this is called a linear equation because when you plot it, the result is always a straight, flat line. We can create a plot by choosing two x and y pairs which solve the equation and then drawing these points on an axis. Then we'll join the 2 points with a straight line, and this is the equation visualized. Now, for any other pair of x and y we choose, we know for certain that the point will land somewhere on this line as long as the pair satisfies the equation. But things get much more interesting than this. The trouble starts when you're not just trying to reach one total, but 2 at the same time. Let's say now you also want the total number of coins to be exactly 11. Suddenly, you are not just solving for how to make 23 cents, you also have to make sure the nickels and pennies together add up to 11 coins. This is where things stop being simple arithmetic and start dipping into real linear algebra territory. Since it is getting a bit more difficult to simply guess the response, we need a systematic way to find out a pair of x and y which solves both equations at the same time. And to do this, we'll use an easy technique with a fancy name. Gaussian elimination is the process of subtracting multiples of one equation from another to try to narrow down the value of one variable. In our case, we'll simply subtract the second equation from the first one and we'll end up with a single variable linear equation. If you don't know how to solve this, then you are probably as bad at math as my 6-year-old son. For the rest of us, the solution should be at least familiar. We'll divide both sides by 4 to get the value of x, and then we'll use the value of x in the second equation to find y. Now, in all fairness, getting to the solution isn't such a big achievement. This technique has been around for over 2000 years. It was first described in ancient China long before anyone used the term linear algebra. Then, it was independently developed later by European mathematicians in the 18th century, so we aren't really operating with cutting-edge ideas here. Now, this is where things get interesting and you should pay attention. This is one of those moments when you stop paying attention in class for a second and then all of a sudden the teacher is talking in a different language and he jumps from counting coins to building rockets. What we've done so far is called a row picture, where we are looking at each equation as a line and the point where those lines meet is our solution. The column picture assumes that instead of having two separate equations, we have only one equation where the numbers from the columns become vectors. So each column represents the direction and scale of one variable, and our goal is to find how much of each vector we need to combine to reach the target point. The good news is that vectors can be plotted as well, so we can solve this in a visual manner. We'll first use the vector values to draw their representation on the plot and add in the point we are trying to reach. Then, in a manner similar to adding coins, we can add and combine vectors together to get to that specific target. So we visually solved our equation by adding 3 vectors for the x value and 8 vectors for the y value. If we now update these values in our equation, we need to multiply a scalar, which is basically a single number, by a vector, so we simply multiply it by each number in the vector. We are then left with 2 vectors that have to be added together, so we'll add the individual elements of each vector. These are the basics of linear algebra, but you might be asking yourself why this really matters. Well, it matters because everything that moves, rotates or changes in a program depends on it. If you've ever seen a character move across the screen, a camera pan in a 3D game, or a robot arm pick up an object, you've seen linear algebra at work. In graphics, for example, your computer doesn't see an actual cube, but a bunch of coordinates in 3D space, which are manipulated by applying a series of linear transformations. Machine learning isn't much different. All those fancy models and buzz
What you're looking at right now is something called quaternion multiplication. Or rather, you're looking at a certain representation of a specific motion happening on a 4-dimensional sphere.
How heavily is used in graphics and robotics. Interesting. Why you don't have to look like this? You do know that, right? Whatever. You don't have to look like a complete pathetic bumperclut. Linear algebra is so down the line. It's crazy. I don't really need it much. Okay, what is AQI?
Let's talk about AQI. What do these numbers mean? When the sky looks like this, you can just see the particulate matter in the air, and that's what we're all breathing. But when the sky gets like this, we throw out the AQI scale at you with numbers of 100, 200, and that sort of thing. So
Okay, let's do some flat out research. Yeah, it's going to be data science. What else? SAS.
So what do these numbers mean? Well, the AQI measures the amount of particulate matter in a cubic meter. So you take a cubic meter of air and then you count how many particles are in there. Now, when the AQI is on the good scale, there's always particulate matter in the air, it's 12 or less. If you have 12 of those little particles in the air, in a cubic meter of air, it equals an AQI of 50 or less. That's good, because like I said, there's always some particulate matter in the air. When it gets up to 35, that's in that marginal category. That equals an AQI of 100. You start getting more into the air, and that becomes unhealthy for sensitive groups. And then you have 55 of those particles in a cubic meter of air, and that gives you an AQI of 150. The scale isn't straight scale. As it goes up to...
Let's see New Delhi. How do I display? Bro, literally imported it. What do you mean? Okay, cool. Yeah. Let's go pip install matplotlib. Yeah, why not? So this data still contains hardly air quality of an environment collected across major cities in New Delhi. Okay. I mean, Delhi actually looks like that, probably. I don't know. High-level models, like, the fuck is that?
Hi everyone! Welcome back to another video in our machine learning series. In this video, we'll learn yet another popular model ensembling method called gradient boosted trees. If you haven't already, check out our previous videos to learn about random forests, where we introduce the concept of model ensembling, as well as decision trees, where we talk about the building blocks of these models. In this video, we'll use gradient boosted trees to perform classification, specifically to identify the number drawn in an image. We'll use MNIST, a large database of handwritten images commonly used in image processing. It contains 60,000 training images and 10,000 testing images. Each pixel is a feature, and there are 10 possible classes. Let's first learn a bit more about the model. Gradient boosted trees and random forests are both ensembling methods that perform regression or classification by combining the outputs from individual trees. However, gradient boosted trees and random forests differ in the way the individual trees are built and in the way the results are combined. As you already know, random forests build independent decision trees and combine them in parallel. On the other hand, gradient boosted trees use a method called boosting. Boosting combines weak learners sequentially so that each new tree corrects the errors of the previous one. Weak learners are usually decision trees with only one split, called decision.
Give me this. Where can I search? Fuck you. Can I get some Okay. Okay, extreme gradient boosting is a popular open source machine learning library designed to improve upon traditional gradient boosting framework. It is widely used in data science and machine learning. Competition due to high accuracy and efficiency in handling large database. During this lab, you will learn the foundational introduction. Boosting is a machine learning technique that combines several weak learners models with significantly better accuracy than randomly guessing, creating a strong learner. The weak learners are trained iteratively and not each step. The algorithm gives more weight to the misclassified example. This allows the subsequent learner to focus on the more difficult examples and improve the overall performance of the model. Boosting algorithms are widely used in both classification and regression tasks and have been shown to achieve state-of-the-art results of the various datasets. Some popular boosting algorithm includes AdaBoost. Okay, what the fuck? So we have a boosting has something to do with cross-validation. Fuck, it's difficult, what? I didn't realize it's actually difficult. I'm supposed to model that? I don't know.
Stumps. So the first step is to fit a single decision tree. We'll evaluate how well this tree does using a loss function. There are many different loss functions we can choose from. For multi-class classification, cross-entropy is a popular you can choose from.
Where do I write all of this shit? This is the AI research book that I need to learn all the machine learning concepts anyway.
For multi-class classification, cross-entropy is a popular choice. Here's the equation for cross-entropy, where P is the label and Q is the prediction. Basically, the loss is high when the label and prediction do not agree, and the loss is 0 when they're in perfect agreement. Now that we have our first tree and the loss function we'll use to evaluate the model, let's add in a second tree. We want the second tree to be such that when added to the first, it lowers the loss compared to the first tree alone. Here's what that looks like, where eta is the learning rate. We want to find the direction in which the loss decreases the fastest. Mathematically, this is given by the negative derivative of loss with respect to the previous model's output. Therefore, we fit the second weak learner on the derivative of L with respect to f of 1. For m, we
I think I'm done. Oh, it's close to being. I'm gonna cut it exactly at 6 hours. So this is my AI notebook. I write all of my AI research and whatnot. And this is my, yeah.